Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, let me know in the chat quickly if all of you can hear me, if I'm perfectly audible, visible to everyone. Quickly, let me know in the chats. Quickly, let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Welcome back, guys. Welcome back. Welcome back. Welcome back. So dear students, as you all must be knowing, till now we are done with 2 sessions of the chapter Chemical Kinetics, right? And today it's going to be the last session. It is going to be the last session of the chapter. And basically we are going to complete this particular chapter in the today's session. Yeah? Perfect. So are you guys done with the first 2 sessions of kinetics? Have you watched them? Have you watched the first 2 sessions of the kinetics chapter? Say yes or no in the chats. Say yes or no in the chats quickly. Are you done with the first 2 sessions? And related to All India Test Series, which we have launched, right? Its syllabus I'll be letting you know today, right? In the Telegram group. I'll be letting you know the syllabus for the upcoming tests for the All India Test Series. In the Telegram group, I'll be mentioning that. Sir, Hindi में session कब होगा? हिंदी में session नहीं होगा. This is the English channel, right? If you want to get trained in Hindi or English, there are other channels of Unacademy too. Okay? You can consult them. Perfect. So without wasting a lot of the time, let's get going and let's get started with the today's session. But before that, the ones who have not subscribed to the channel yet, I would want every one of you to subscribe to the channel right now so that you remain updated about all the sessions which we take live on this particular Unacademy NEET English channel, right? So do like the session, do share the video with everyone, let everyone get benefited out of the sessions, and my dear students, at the same time, if you have not subscribed to the channel yet, please and please do subscribe to the channel as well, right? So that you'll remain updated about the sessions, about the chapters which we keep on completing on YouTube, that too absolutely free of cost. Yeah? Perfect, guys. So, if you remember, in the last session, we completed till zero order reactions. So, in this particular session, I'm going to start with the first order reaction. Okay? What are first order reactions and what all characteristics we have to remember about first order reactions, what all different types of questions can be asked from first order, all those things I'm going to discuss one by one in detail, right? Perfect, guys? Yes, absolutely. Next chapter is going to be your GOC. So IUPAC nomenclature, I'm taking day after tomorrow. It's going to be a one-shot video. The thumbnail, I believe it's already out. You would have seen that too. Perfect, guys. So let's get going. Let's get started. All right. Just give me a second. Just give me a second. Just give me a second, guys. All right, so let's talk about the first order reaction. What first order reactions are all about and how do we get the integrated rate equation for the first order reaction. That's important. My dear students, look at the definition. First order reaction, it is that particular reaction in which the rate of the reaction varies linearly with the concentration of reactant. Now, you must be thinking what is meant by that. For example, I'm taking a balanced chemical equation A gives B. Let's assume this is a balanced chemical equation whose rate constant, for example, is K. And at the same time, I'm assuming that the order of the reaction is 1, right? This is something which I'm assuming. Order of the reaction is 1. Now, my dear students, if I write the rate law for this particular reaction, how do I write it? I'll be writing rate of the reaction is equal to, it's going to be rate constant multiplied by concentration of A raised to the power order, that's 1. Okay. Now, my dear students, look at this particular expression. Look at this particular rate law. If you double the concentration of A, the rate of the reaction automatically doubles. If you triple the concentration of A, the rate of reaction automatically triples. If you make the concentration of A 4 times, the rate of this particular reaction will become 4 times. Any such reaction in which rate of the reaction varies linearly, with the concentration of reactant, we call that particular reaction as the first order reaction. Any such reaction in which rate of reaction varies linearly with the concentration of reactant, we call that particular reaction as the first order reaction, right? Very, very simple and basic. Perfect. If you double the concentration of A, the rate will double. If you triple the concentration of A, the rate will triple. If you make it 4 times, the rate will become 4 times. So rate is varying linearly with the concentration of reactant. Any such reaction in which rate varies linearly with the concentration of reactant, what do you call that reaction as? You call that particular reaction as the first order reaction, right? Now, my dear students, what exactly we are going to get? The way we derived the integrated rate equation for the zero order reactions, in the similar way, I'm going to derive an expression, which is what you call as integrated rate equation, which will be perfectly valid only for the first order reaction. And from that particular expression, you can solve almost all the questions. Let's try to derive that expression. That's important, right? Try to understand what I'm going to say. My dear students, the reaction is A gives B. It's a balanced chemical equation. That's something which I'm assuming. Now, at time t is equal to 0, let's assume the initial concentration of reactant is A naught. This has to be 0. Now, you know, as the reaction proceeds, the concentration of reactant, it decreases with time. Let's assume at time t, the concentration of reactant left, that is 80. Let's assume that the concentration of reactant left in the container at time t, that is, for example, 80. And similarly, for example, the concentration of product formed at time t, that I'm representing with Bt. So you have to be clear with all these terminologies first of all. So what is A naught? A naught is nothing. It is the initial concentration. It is the initial concentration of reactant. It is the initial concentration of reactant at time t is equal to 0, right? What is AT? AT is basically the concentration of reactant. It is the concentration of reactant left at time t. Similarly, what is Bt? Bt is the concentration of product. Bt is the concentration of product formed at time t. Formed at time t. And what is K? K is the rate constant of the reaction. K is the rate constant of the reaction. And what about the order of the reaction? Order of the reaction which I'm taking over here, that's 1. Okay. Now try to understand. First thing, I'll be writing the rate law for this particular reaction. How do I write the rate law? Rate law for the reaction. Rate is equal to rate constant multiplied by concentration of A raised power 1. This is how you write rate law for this particular reaction because its order is 1. Now, my dear students, is there any other way to calculate the rate of reaction? Absolutely. You can calculate the rate of reaction with the help of differential form as well. You can calculate rate of reaction with respect to reactant. It is just you have to start with minus sign, right? 1 divided by stoichiometric coefficient is 1. Okay, then it's going to be change in the concentration of A divided by dt. Perfect, right? Now, my dear students, from this particular result, from this particular expression, I'm going to get one very, very, very important expression. And what is that important expression going to be? For that, I would need a new slide over here. Understand. What did I get? I got something like this. K multiplied by concentration of A raised power 1 is equal to minus times d of A divided by dt. This is something which I got till now. Perfect. Right? Now, dear students, try to understand few more things. I can write it like this as well. I can write it dA divided by dt. dA divided by dt is equal to minus times K, or let me write it like this, just a second. I can write it like this, minus, or leave minus aside, I can write dA divided by concentration of A. dA divided by concentration of A is equal to minus K multiplied by dt, right? I'm just separating the variables, nothing else. See, what did I do? I took this A in the denominator, took this dt over here, and it's going to be minus times. So dA divided by dt is equal to minus k dt. Perfect. Now what exactly I'm going to do? I have to get the integrate rate equation. My dear students, I'll be integrating on both the sides. Over here, I'm integrating with respect to the concentration of A. And concentration of A, as you see, it is changing from A0 to AT. Concentration of A is changing from A0 to AT. And right here, I'm integrating with respect to time. And look at the time, from 0 to t, right? So the limits are going to be from 0 to t. Now, if you want to check whether the limits you have given, those are correct or not, look at this particular thing. At time t is equal to 0, the concentration of reactant was A0. At time t, the concentration of reactant was AT. Perfect. Now, you must be knowing integral of dA divided by A. Integral of dA divided by A. What is it going to be? Integral of dx by x. That's going to be ln of x. Integral of dy divided by y. That's going to be ln of y. In the similar way, integral of dA divided by A. It's just going to be ln of A. It's going to be ln of concentration of A. Under the limits A0 to AT. And on right side, minus will come out, k will come out. Integral of dt is t, upper limit, lower limit, so it's going to be minus kt in short, right? Now guys, give the upper limit, give the lower limit. It's going to be ln of AT minus ln of A0 is equal to minus kt, or you can write it like this. You can write it ln of AT is equal to ln of A0 minus kt. Well, this is the first way of writing the integrated rate equation for the first order reactions. This is the first way of writing the integrated rate equation for the first order reaction. In zero order reaction, it used to be AT is equal to A0 minus KT. And here in the first order reaction, it's going to be ln of AT is equal to ln of A0 minus KT. Correct? This is the first expression. Well, you can write the integrated rate equation in different formats as well. This is one of the format. This is one of the format in which you are writing the integrated rate equation. What about the other formats? Have a look. My dear students, how do you convert a ln into log? Instead of ln of AT, I'll be writing 2.303. It's going to be log of AT. This is how you convert a ln into log, as simple as that. Similarly, instead of ln of A0, I'll be writing 2.303. It's going to be log of A0. And with it, you have got minus KT as well. Yeah? Now do one thing. Divide throughout by 2.303. In this particular equation, if you divide throughout by 2.303, what do I get? I'll be getting something like this. Log of AT is equal. It's going to be log of A0 minus K divided by 2.303 multiplied by T. This is one more way to write the integrated rate equation for the first order kinetics. One more way of writing the integrated rate equation. Log of AT is equal to log of A0 minus K divided by 2.303 multiplied by T. So how many forms of integrated rate equation we got till now? This was the first form. This is the second form. Correct? First form, second form. I believe it's clear till here, right? I believe it's clear till here. Is it? Is it, guys? Is it clear to everyone quickly? Quickly in the chats. Yeah? Did you get to know how did we get these two equations? These are very, very, very important. There are some more ways to write the integrated rate equation for the first order reactions. Let's exactly have a look what those ways exactly are. And all the forms of integrated rate equation of the first order kinetics, they are very, very, very important. So you have to remember them one by one. First, ln of AT is equal to ln of A0 minus KT. Second, log of AT is equal to log of A0 minus K divided by 2.303 multiplied by T. Now let's have a look on few more expressions of the first order kinetics. Have a look, guys. Understand properly what exactly I'm going to say. If you look at this particular equation, the one which I'm representing with star, right? What exactly I'm going to do? I'm going to multiply this equation by minus. I'm going to multiply this particular equation by minus. Multiplying this equation by sign minus. It will come out to be ln of A0 minus ln of AT. It will come out to be equal to KT. It will come out to be equal to KT, right? Now, dear students, ln of m minus ln of n comes out to be ln of m divided by n, right? And this is equal to k times t. Perfect. Now, you can write it like this. You can write k is equal to 1 divided by t ln of A0 divided by AT. This is one more expression, right? This is one more way of writing the integrated rate equation for the first order kinetics. So this is the third expression of writing the same thing. This is integrated rate equation. Even this is. These are the different formats of integrated rate equation, nothing else. Okay? At the same time, this was the third expression. This was the third one. Now, my dear students, you can write the same equation like this as well. K is equal. This form is in terms of ln. Now convert it in logarithmic form. So K is equal. It's going to be 2.303 divided by T. Now it's going to be log of A naught divided by AT. This is the most important form of the integrated rate equation, which I'll be using in majority of the questions, and I'll be calling this expression as the fourth expression. So this is the fourth expression of writing the integrated rate equation, right? Is that it? No, that's not it. There is one more way. There is one more way, guys. Try to understand. Try to understand what exactly I'm going to do. If you look at this particular result, the star one, if you look at this particular result, the star one, ln of m minus ln of n, it's going to come as ln of m divided by n. So it's going to be ln of AT divided by A naught is equal to minus KT, right? The base here is how much? The base here is E. The base here is E. So my dear students, how do I write it? How do you convert a ln into exponential form? How do you convert logarithmic form into exponential form? For example, you have got something like this. Ln of x to the base y is equal to z. Ln of x. For example, you have got something like this. Just a second. Ln of x to the base a, for example, is equal to z. How do I convert it into the exponential form? I'll be simply writing x is equal to e raised power z. I'll be writing x is equal to e raised power z. This is how you convert ln into exponential form. Correct? Similarly, you have got a similar type of equation like this. Ln of something to the base a is equal to minus kt. Can't I write? Can't I write at divided by a naught will be equal to e raised power minus kt? Absolutely, it will be e raised power minus kt. Now, why did I do it? Because I wanted to get one more equation, and the equation is something like this. Try to get it properly. The equation is something like this. I'll be writing at is equal to a naught e raised power minus kt. This is one more expression. This is one more way of writing the integrated rate equation for the first order kinetics. So these are in total some 5 different forms by means of which you can write the integrated rate equation. Perfect. So is this clear till here, whatever I taught you? My dear students, you have to remember them. They should be on your tongue at every time. They should be always at the tip of your tongue. First one, in terms of ln. Ln of AT is equal to ln of A naught minus KT. Second one, log of AT is equal to log of A naught minus K upon 2.303 into T. Right? Similarly, third one, K is equal to 1 by T ln of A naught by AT. Next one, K is equal to 2.303 divided by T log of A naught divided by AT. Next one, AT is equal to A naught E raised power minus KT. These are the different forms of the same equation. I hope I'm clear till here. Yeah? Is it clear? Is it clear, people? Quickly. Right? I hope all these things are absolutely clear to you, right? So these are the equations which I want every one of you to remember, and all these equations are valid for the first order reactions. Where do we use them? How do we use them? That's a separate debate which I'll be letting you know in some time. But before talking about those things, till now, whatever equations I have given you, how do we make different types of graphs, right, for the first order reaction? Try to understand what exactly I'm going to say. Graphs which are based on first order reaction. Graphs are related to first order reaction. There are a lot of graphs, but right now I'll be showing some 4 to 5 graphs. The other graphs will be discussed too, but after some time. Okay? My dear students, the first graph which I'm plotting, that's going to be between rate of reaction versus concentration of reactant for the first order reaction. You should be able to make this particular graph on your own. You know, as far as the rate law is concerned for the first order reaction, R is equal to K, it's going to be concentration of A raised power 1. Now it's very simple. Rate of the reaction you are plotting along y-axis. Concentration of reactant you are plotting along x-axis. So this is your M. Y is equal to mx. Is it going to be a straight line passing through origin? Absolutely, it's a straight line passing through origin, right? If you ask me, what about the slope of this particular curve? Slope is basically m, which is k over here. Slope is represented by m, right? Slope is represented by m, and m is k in this particular case. So this is the first graph, which is perfectly valid for the first order reactions. Number one. Number two. For example, I am plotting one more graph. The graph has to be between ln of AT versus T. Ln of AT versus T. What is the equation? We know ln of AT is equal to ln of A naught minus KT. So this is the equation, correct? Ln of AT you're plotting along y-axis. So instead of ln of AT, I'm writing y. Time you're plotting along x-axis. So instead of t, I'm writing x. So this is your m. The sign here is minus, and this whole term is going to be your c. And over here you've got equal sign, and this has to be plus. So y is equal to minus mx plus c. Y is equal to minus mx plus c. What is the nature of the curve? Minus mx plus c, the curve will be like this, right? What about the slope of this particular curve? Slope of this particular curve directly is equal to minus k. And if you ask me about the intercept, the distance from the origin to the point from where the curve starts, intercept, which is denoted by c, that's actually equal to ln of A naught. So this is one more graph, which is perfectly valid for what? It is again valid for the first order reactions, right? Now, my dear students, for example, you're plotting one more graph. The graph is between log of AT versus T. Log of AT versus T. One equation I gave you a few minutes back. That was the log of AT is equal to log of A naught minus K divided by 2.303 multiplied by T. This was the equation which I gave you a few minutes back. Now try to understand. Log of AT you're plotting along y-axis is equal to this time you're plotting along x-axis. So this is your x. So this whole term has to be your minus m. This whole term is equal to minus m. And this is basically c. The sign over here is positive. So it's again y is equal to minus mx plus c. So minus mx plus c graph is like this. So what about the slope of this particular curve? Slope of this particular curve, as you can see over here, it is minus k upon 2.303. What about the intercept? Intercept is basically represented by c, and c value is nothing, that is log of A naught. So this is one more graph which can be asked in the question, right? This is one more graph which can be asked in the questions. And I'll show you the questions after some time, but there are a lot of other things which needs to be discussed too. Okay, let's try to complete everything step by step. Now we will at the same time. For example, you have to make a graph. The graph is between AT versus T. The graph is between AT versus T, right? 2 minutes back only I gave you one equation. I told you AT is nothing, that is A naught e raised power minus KT. AT is equal to A naught e raised power minus KT, right? Now, as you can see over here on this curve, AT you are plotting along which axis? AT you are plotting along y-axis, right? This is going to be y is equal to A naught, that's a constant, for example, k, e raised power minus e raised power minus kt. T you are plotting along x-axis, so it's going to be e raised power minus x format. Y is equal to k e raised power minus x format. Do you remember what will be the nature of the curve? Do you remember what will be the nature of the curve? Y is equal to e raised power minus x type. Y is equal to e raised power minus x. Is it going to be the exponential decrease form? Absolutely, it will be the exponential decrease form. It will be exponentially decreasing. Exponentially decreasing, right? And my dear students, this graph, it is not going to touch the x-axis. It is not going to touch the time axis. Why is that? There's a reason, which I'll tell you in some time, right? This is one more graph, which you have to remember for the first order reaction. AT versus T. It's exponentially decreasing curve, right? But do remember this particular graph, it's not going to touch the time axis over here. What is the logic behind that? Why it's not going to touch? There's a reason, which you'll get in some time, right? So these are the 4 graphs which I wanted to discuss with you, right, before doing the other things. Ln AT versus T, log AT versus T, then you have got rate versus concentration, you have got concentration versus time. So these are few graphs which you need to remember, okay? And directly questions will be asked from these graphs. Directly questions will be asked from these graphs. How exactly? Again, you'll see that in some time. Now try to understand few more important features of the first order reactions. So till now, I only talked about the integrated rate equation, right? Integrated rate equation I taught. Second, my dear students, the second parameter, that is the half-life. Half-life. Do you remember how did we define the half-life? The time taken to complete 50% of the reaction. The time taken to complete 50% of the reaction. Or you can define it the time in which the concentration of reactant reduces to half. The time duration in which the concentration of reactant reduces to half, right? Or you can simply say the time duration in which the concentration of reactant reduces from A0 to A0 by 2, right? Let's try to understand what this half-life, how this half-life is calculated for the first order reactions. Try to understand. My dear students, we have got the reaction. A gives B, whose rate constant is K. Imagine that at time t is equal to 0, the initial concentration of reactant is A0. Now, what is going to happen with time? When the reaction proceeds, the concentration of reactant will keep on decreasing with time, right? The concentration of reactant will keep on decreasing with time. My dear students, at time t is equal to t half, at time t is equal to t half, when 50% of the reaction would have got completed, when 50% of the reactant would have got converted into product, can you let me know what will be the concentration of reactant left in the container? The concentration of reactant left in the container is simply going to be A0 by 2, because 50% of the reactant has got converted into product. So this is the concentration of reactant left at time t, and the concentration of reactant left at time t, that is represented by what? That is represented by AT. So simply I got one condition over here. This is one condition which I got. At time t is equal to t half, AT value is equal to A0 divided by 2, right? Now, dear students, if I use the integrate rate equation, do you remember this particular equation I told you a few minutes back? T is equal to 1 divided by K, ln of A0 divided by AT. This was one of the forms of integrate rate equation. My dear students, if I put this particular condition in this equation, if I put these conditions in the equation, what I'll get? So instead of T over here, I'll be writing T half. Instead of T, I'm writing T half is equal to 1 divided by K. It's going to be ln of A0 divided by AT value over here is equal to A0 divided by 2. AT value is equal to A0 by 2. So A0 A0 gets cancelled. So you got to know T half is equal to ln of 2 divided by K. And ln 2 value you already know, that is 0.693 divided by K. So this is one expression which you need to remember, by means of which you can calculate the half-life of the first order reaction. So half-life for the first order reaction is ln of 2 by K, or you can say 0.693 divided by K. Whereas if you compare it with the zero order used to be A0 divided by 2K. T half is equal to A0 divided by 2K for zero order reactions. But here, as you can see, T half is equal to ln of 2 by K, or you can say 0.693 divided by K. Perfect. Now, my dear students, if you look at this expression, in this expression, do you see the A0 term? Do you see the initial concentration of reactant? No. So I would categorically say half-life of the zero order reaction. Half-life of the first order reaction is independent. It is independent of the initial concentration of reactants. It is independent of the initial concentration of reactant, right? But it's valid perfectly for what? It's valid perfectly for first order reaction. Yeah? Right, people? Now, if I ask you to plot a graph, between T half-life of the reaction versus initial concentration of reactant, what will be the nature of the curve? Since I told you T half, it is independent of initial concentration of reactant. It is independent of any concentration term. So on changing the concentration of reactant, nothing happens to the half-life. It remains the same. It's constant. If you increase or decrease the concentration of reactant, nothing is going to happen to the half-life of the first order reaction. So this curve is valid for the first order reactions. Whereas if you remember your zero order reactions, T half used to be equal to A0 by 2K. And if you remember, when I plotted a graph between T half versus A0 for a zero order reaction, it used to be like this, whose slope used to be equal to 1 divided by 2K. This was for zero order reaction, but this is for first order reaction. You know it, right? Simple. So this was the half-life. Half-life expression I want you guys to remember from now onwards. T half is equal to ln 2 by K. It's equal to 0.693 divided by K. So this was the second parameter which I wanted you guys to remember. The third parameter. The third parameter for the first order reaction. What is that? That's completion time. What used to be the completion time in zero order reaction? It used to be A naught by K. It used to be A naught by K. How do we get the completion time in the first order reaction? This is important. Have a look exactly what I'm going to say. This is important. My dear students, you have got the reaction again A gives B, whose rate constant is K. Order of the reaction is 1. It's understood it's a first order reaction. Now at time t is equal to 0, assume that the initial concentration of reactant is A naught. So this has to be 0, right? Now with time, what is going to happen? With time, I must say, the concentration of reactant will keep on decreasing. With time, the concentration of reactant will keep on decreasing. If I say at time t is equal to t 100%, at time t is equal to t 100%, what is t 100%? The time taken to complete 100% of the reaction. The time taken to complete 100% of the reaction. The time duration in which 100% of the reactant would have got converted into product, right? The time duration in which the 100% of reactant would have got converted into product. So my dear students, at t is equal to t 100%. If 100% of reaction gets completed by chance, right? That means 100% of reactant would have got converted into product. So can I say the concentration of reactant left at that time will be 0, and the concentration of reactant left at any time is represented by AT. So I would say at time t is equal to t 100%, AT value should be equal to 0. The concentration of reactant left in the container should be 0, because I'm assuming that 100% of reactant has got converted. Yeah, I got one condition here. Condition is at time t is equal to t 100%, AT value is equal to 0. What does it mean? My dear students, use the integrated equation. T is equal to 1 divided by K. It is the ln of A naught divided by AT. Right? If I put this particular condition in this expression, instead of T, I'll be writing T 100% is equal to 1 divided by K. It is the ln of A naught divided by, what is AT? AT value is 0. AT value is 0. Division by 0 is infinite. So can I say this whole term will approach towards infinity? This whole term is approaching towards infinity. What does it mean? It means that a first order reaction takes infinite time to get completed. A first order reaction to get 100% completed will take infinite time, right? A first order reaction, it takes infinite time to get 100% completed. What does that mean exactly? That means a first order reaction, it never undergoes 100% completion. A first order reaction, it never undergoes 100% completion. Do you remember a few minutes back only I made one graph? The graph was like this. AT versus T. This was the graph. And the nature of the graph was like this. It was like this, right? This point represents time t is equal to 0. At time t is equal to 0, the concentration of reactant is A naught. Now with time, the concentration of reactant is decreasing. I told you that this curve is not going to cut the time axis. Why? Because if this curve cuts the time axis, at that point, the concentration of reactant would become 0. At that point, the concentration of reactant would become 0. That means the reaction has got 100% completed. But a first order reaction never undergoes 100% completion. So this particular graph, it is not going to cut the time axis. If it cuts the time axis, that tells you that the concentration of reactant has reduced to 0, right? Which is not possible. That means 100% reaction has got completed, which is not possible in case of the first order kinetics, right? So do remember, a first order reaction, it never undergoes 100% completion. This is one more important point which I wanted to share with you, right? Is it clear till here, people? Quickly. Is it clear till here? Is it clear till here? Quickly. Was this the fourth point? No, it was the third point. Now, let's talk about the fourth point related to the first order reactions. What is that? What is that? That is degree of dissociation. That is degree of dissociation. How do we get the degree of dissociation for the first order reactions? If you remember, In case of zero order reactions, we also calculated the degree of dissociation. It used to be equal to Kt divided by A naught, right? Now let's get to know in the first order reactions how to get the alpha value. Let's get to know how do we get the alpha value. See guys, the reaction again which I'm taking, that's A gives B, whose rate constant is K. It's the first order reaction, right? At time t is equal to 0, the initial concentration, or you can say initial moles of reactants, that's A naught, for example. Initial concentration or initial moles of reactant, that's A naught. At time t, the concentration of reactant left or the moles of reactant left at time t, that's equal to AT. Correct? What do we need to get? I need to get the value of alpha. How do you get the value of alpha? What is alpha? Alpha is number of moles of reactant dissociated into product by initial moles of reactant, right? Alpha is equal to ND divided by NI. Number of moles of reactants dissociated into products divided by initial moles of reactants. Now, my dear students, if I ask you, how many moles of reactants have got dissociated into products? Initially, I started with A naught moles. Initially, I start with A naught moles. I am left with 80 moles. So, how many moles of reactants have got converted? It is A naught minus 80. So, these are the moles of reactants basically which have got dissociated into products, right? Which have got dissociated into products divided by what is Ni? Ni represents initial moles of reactants. Initial moles of reactants are simply A naught, right? Perfect. So, my dear students, alpha is equal. It has to be A naught minus. What is 80? 2 minutes back only I told you the value of 80, which is A naught e raised power minus Kt, right? Divided by A naught. My dear students, if I take A naught common in the numerator and denominator, A naught gets cancelled, I'll be getting the value exactly 1 minus e raised power minus Kt. So, this is the expression. This is the expression to calculate the degree of dissociation for the first order reaction, right? This is how you calculate the degree of dissociation for the first order reaction. Alpha is equal to 1 minus a raised power minus Kt. And this particular result, it's valid for the first order reaction. If I ask you, what was the expression for zero order reactions? For the zero order reactions, alpha was equal to Kt divided by A naught, if you remember, right? Now, my dear students, there is one thing which I want you guys to have a look on. In case of zero order reactions, alpha was dependent on the initial concentration of reactant. Here, alpha is independent of the initial concentration of reactant. So, do remember, take a note of this particular statement, that the degree of dissociation alpha is dependent or independent? Is independent. It is independent on the initial concentration of reactant, right? But it's valid only for the first order reactions. But in case of zero order reactions, it is absolutely dependent, right? Perfect. Now, again, one more thing. If I want you guys to plot a graph, between alpha versus A naught, in case of zero order reaction, it was rectangular hyperbola. But here, what will be the nature of the curve? I told you in case of first order reactions, if you increase or decrease the concentration of reactant, nothing happens to the value of alpha. The value of alpha will remain the same. This particular result, it's valid for, this particular graph is valid for the first order reaction. I hope this is clear to everyone, right? So this is how you get the degree of dissociation for the first order reaction. Is that clear? Let me know once in the chats quickly. Let me know once in the chats quickly. See, degree of dissociation of a zero order reaction, that depends on A naught. Whereas degree of dissociation for the first order reaction, it is independent. That does not depend on the A naught. Okay? Yes, Prajwal, you can go ahead with the doubt. What is the doubt? What is the doubt? So till now we are done with the 4 characteristic features of the first order reaction. The 5th characteristic feature which I'm writing on my own. What is that? The 5th characteristic feature I'm going to let you know. It is basically the time taken to complete X% of a first order reaction. The time taken to complete X% of the first order reaction. How much time does it take to complete a certain percentage of a first order reaction? For example, Prajwal, just wait for it. I'm going to derive that expression as well, right? I'm going to derive that expression as well. This is something which you were talking about, right? Is this the topic which you are waiting for? Time taken to complete X% of the first order reaction. That means time taken to complete, for example, 10% of first order, 20%, 30%, 50%, 60%. How do we calculate it? Try to understand. Or you can say time taken to complete a certain fraction of reaction. Yeah? Try to understand. My dear students, you have got the reaction A gives B, whose rate constant is, for example, K. And this reaction, it follows the first order kinetics. Initially, at time t is equal to 0, let's assume that the initial concentration of reactant is A0. This is 0. This is something which I'm assuming. Now, my dear students, let's assume that X% of the reaction has got completed. The time taken to complete X% of the reaction, I'm representing that with Tx%. Time taken to complete X% of the reaction is equal to Tx%. Now, what does it mean that X% of the reaction has got completed? What does it mean? That means X% of the reactant has got converted into product. That means X% of reactant has got converted into product. So at time t is equal to Tx%, can you let me know the concentration of reactant left in the container? See, initially I started with A0. This was my initial concentration. Now, X% of the reactant is getting converted. X% of the reactant is getting converted into product. So I'll be left with A0 minus X% of A0. A0 minus X% of A0. This is the concentration of reactant left at time t, which I'm representing with AT. Right? Now, let's get its exact value. So A0 minus, this is going to be X divided by 100 multiplied by A0. Or you can say, you can take A0 as common. You can take A0 as common. It's going to be 100 minus X divided by 100. This is equal to AT. This is equal to AT. So at time t is equal to Tx%, at time t is equal to Tx%, this is the concentration of reactant left in the container. This is the concentration of reactant left in the container. Now do one thing. Use the integrate rate equation. That is T is equal to, let's use this expression, 2.303 divided by K. It is the log of A0 divided by AT. Correct? So I would say, if I use this particular condition, this is my condition. This is my condition. If I use this condition in this expression, then instead of T, I'll be writing Tx%. So time taken to complete X% of the reaction is equal to 2.303 divided by K. It's going to be log of A0 divided by, what is AT? AT is nothing, that's A0 multiplied by 100 minus X divided by 100, right? So A0 and A0 gets cancelled out. So time taken to complete X% of the reaction, it is always equal to 2.303 divided by K, and it's going to be log of 100 divided by 100 minus X. This is the formula. This is the expression which you guys are going to remember to calculate the time taken to complete X% of the first order reaction. Yeah? Right, people? Is it clear? So, my dear students, when do we use this particular expression? For example, you have to calculate the time taken to complete 10% of the first order reaction. You'll just put the value of X as 10. You'll just put the value of X as 10. Time taken to complete 20% of the first order reaction. Put the value of X as 20. Right? 30% of the reaction. Put the value of X as 30. You'll be getting the time taken to complete X percentage of the reaction. Yeah? Right, people? Perfect. Now, there is one expression here. There is one important thing which you need to understand here. In this expression, do you see the concentration of reactant anywhere? Do you see A0 anywhere? In this particular expression, do you see A0 term anywhere? Just tell me that. Just tell me that. You do not see A0 term here in this expression. What does it mean? It means that time taken to complete X% of the reaction, time taken to complete X% of the first order reaction, it is independent of the initial concentration of reactant. I'm going to write this particular expression here, or maybe I've already written it. Time taken to complete a certain fraction of first order reaction. Or you can say indirectly, time taken to complete X% of the first order reaction. That is independent of the initial concentration of reactant. That is independent of the initial concentration of reactant. My dear students, this particular expression, this particular result, it has got significance as well. It has got significance as well. Try to understand its significance. For example, you have got the reaction like this, A gives B. See what this statement exactly means. You have got the reaction A gives B. Right? You have got the reaction A gives B. Let's say it's a first order reaction, first of all. Absolutely. It is a first order reaction. Now, guys, let's assume the initial concentration of the reactant here is, for example, 5 molar. The initial concentration of reactant is 5 molar. Here, I'm keeping the initial concentration of reactant as 10 molar. I'm keeping the initial concentration of reactant as 10 molar. Now, my dear students, for example, when the initial concentration of reactant is 5 molar, let's assume at that point of time, 10% of the reaction, 10% of the reaction is completed, for example, in 20 minutes. 10% of the reaction is, for example, completed in 20 minutes. Since time taken to complete a certain percentage of reaction, that's independent of initial concentration. No doubt you have kept the initial concentration of reactant as 10 molar here. But again, to complete 10% of this reaction, it will again take 20 minutes only. I hope you got this particular state. So time taken to complete a certain percentage of first order reaction, that is independent of initial concentration of reactant. No doubt you have kept the initial concentration different here, but time taken to complete a certain percentage of the reaction will be same in both the scenarios, no matter what the initial concentrations are, right? Right, people? Is it clear to everyone? Quickly. Is it clear to everyone? Do you know why did I give you this particular concept? Because there was a question asked long back in your JEE examination, and it's a proper NEET standard question. If you got the exact idea of what I said, you're not supposed to use any pen and paper in this question. You can solve it directly. Otherwise, it will take you like 5 to 6 minutes to do the calculations, etc., etc. Look at the question, tell me the answer. Look at the question and tell me the answer. Read the question carefully. The question is the catalytic decomposition of a reactant over gold. It is a first order reaction. So for example, you have got the reaction like this, A gives B. Let me not write the exact reaction, leave that aside. Let's say the reaction is A gives B, and it's following the first order kinetics. It's following the first order kinetics. At the initial concentration of 200 molar, it was 73% decomposed in 100 minutes. So 73% of the reaction was getting completed in 100 minutes. 73% of the reaction is getting completed in 100 minutes, right? Now, my dear students, the question is, how much will it decompose in 100 minutes if the initial concentration was 600 molar? Now, imagine in the same reaction, you are taking the initial concentration as 600 molar. Imagine in the same reaction, you are keeping the initial concentration as 600 molar. Now, he's asking you, in 100 minutes of time, how much reaction would have got completed? Same 73% of the reaction would have got completed. So the answer is 73%. Because I told you 5 minutes back, taken to complete X% of the first order reaction. It's absolutely independent of the initial concentration of reactant. Whatever initial concentration you want to keep it. Nothing will happen to the time taken to complete a certain percentage of the first order reaction. Yeah? Is it clear to everyone? So my dear students, this was our 5th parameter for the first order reactions, right? 5th parameter. Now we have got few more expressions which I would want you guys to remember directly. I'm not going to derive the expressions. I want you guys to remember the expressions and try to use them in the questions. See. Now our sixth parameter for the first order reactions. What is that? Time taken to complete. 75% of the first order reaction. How do you get the time taken to complete 75% of the first order reaction? Do remember, there are few expressions which I want you guys to remember directly. No need of derivation, etc., etc., right? So the first expression is time taken to complete 75%. Time taken to complete 75% of the first order reaction. It is 2 times the half-life. It is equal to 2 times the half-life. Time taken to complete 87.5% of the first order reaction. It is 3 times the half-life. And time taken to complete 99.9% of the first order reaction. It is 10 times the half-life. And all these 3 expressions, these are valid only for the first order reaction. Do you remember them? With the help of these particular results, you can solve the questions in lesser time. You can solve the questions in lesser time, right? The first one, time taken to complete 75% of the first order reaction. That's 2 times half-life. 87.5% of the reaction. That's 3 times half-life. 99.9% of the reaction. That is 10 times half-life. Even you can derive these expressions as well, right? The expression which I gave you a few minutes back, time taken to complete X%. You just have to put the value of X as 75. Then you have to put the value of X as 87.5. Then you have to take the value of X as 99.9. Eventually, you'll get the result, right? But nothing to do with the derivation. Just remember these results. So this was our 6th parameter related to the first order reactions. Now, let's have a look. Where do we use this? Let's have a look. Where do we use all these results? Few questions will do. Then there are few more parameters related to the first order reaction. It's not done yet. It's not done yet, right? There are few more parameters. But before talking about that, let's try to solve some basic questions. The question is, a first order reaction is 75% completed in 100 minutes. So you have got a first order reaction. And it's mentioned that the first order reaction is 75% completed. In how much time? A first order reaction is 75% completed in 100 minutes. He's asking you, calculate the time taken to complete. Calculate the time taken to complete 87.5% of the reaction. This is something which we are supposed to calculate. Isn't it very simple? See guys, time taken to complete 75% of the first order reaction. That's 100 minutes. And you know, this particular thing, it is equal to 2 times the half-life. So 2 times T half is nothing. That's 100. Correct? So from here, you can calculate half-life, which comes out to be 50 minutes. So you got the half-life of the reaction first of all. Why do I need the half-life? Because I'm supposed to calculate the time taken to complete 87.5% of the reaction. You know, it is always equal to 3 times half-life for the first order kinetics. Since half-life you already calculated, that's 50 minutes. The value overall comes out to be 150 minutes. So I'll say 87.5% of the first order reaction will get completed in 150 minutes. I hope this is clear to everyone. I hope this is super clear to everyone, right? Right, people? Let's do a few more questions. Then we'll move on to a few more topics. Then we'll move on to basically a few more characteristics of the first order, right? Look at this particular question. The question says for an elementary reaction, X gives Y plus Z. Half-life is equal to 10 minutes. In what period of time would the concentration of X be reduced to 10% of the original value? Right? Are you understanding this particular question? See, as per the question is concerned, we are given the reaction X gives Y plus Z. It is not mentioned in the question whether the reaction is 0 order, whether it's first order. It's not mentioned. But there is one statement that's mentioned. The reaction is elementary in nature. If you remember, I have told you, in case of the elementary reactions, molecularity is always equal to order. Right? Do you remember? In the last session only I have told you. In case of the elementary reactions, order is equal to molecularity. What is the molecularity of this reaction? Molecularity of this reaction is 1. That means the overall order of this particular reaction, it has to be 1 as well. So it's a first order reaction. It is a first order reaction. Yeah? Right? Nikhil, syllabus I'll be giving in the Telegram group. Right? Tonight. Telegram group. Okay. The reaction which is given to us, its half-life is equal to 10 minutes. Its half-life is equal to 10 minutes. Now, you know, half-life is nothing. It is 0.693 divided by K. That is basically 10 minutes as per the question. So K has to be equal to 0.0693. And its units are going to be simply minute inverse. Right? So this is the rate constant. I first of all calculated the rate constant with the help of half-life. With the help of half-life. Now, what are we supposed to calculate? In what period of time would the concentration of X be reduced to 10% of its original value? Right? So indirectly, he's asking you, how much time will it take for the reaction to get 90% completed? Do you agree with this? Indirectly, he's asking you, how much time would it take for the reaction to get 90% completed? Because when the 90% of the reaction will get completed, that means 90% of the reactant will get converted into product. At that point of time only, 10% reactant will be left in the container. 10% reactant left in the container means 90% reaction completed, right? So he's asking you the time taken to complete 90% of the reaction. So time taken to complete 90% of the reaction will be equal to 2.303 divided by T. It's going to be log of, you can write 100 divided by 100 minus X. 100 minus X, and X is 90. So this is 10, 100 divided by 10 is 10. So you can say time taken to complete 90% of the reaction is equal to, sorry, this is K here. This is K here. So it's going to be 2.303 divided by K. K value already we have calculated 0.0693, and it's log of 10, and log of 10 is 1. So you just need to do a bit of calculation and you'll be getting the time taken to complete 90% of the reaction. Yeah? Is it clear? It's simple, guys, right? So the answer at the end of the question will be 33 minutes. So it will take approximately, not approximately, it will take exactly 33 minutes to complete 90% of the first order reaction. Yeah? Sir, who will teach atomic structure and periodic classification? I will teach atomic structure and periodic classification. No need to worry. Okay? Even I'll teach few chapters of organic as well. Okay, because physical almost we are done with, right? Physical almost we are done. Yeah? Even chemical bonding is also done. Inorganic one chapter is also done. Perfect. So this was the first question, which I gave it to you. All right. Look at this particular expression. Look at this particular expression, my dear students. Look at this particular equation. The equation is, an organic compound undergoes a first order decomposition. Time taken for its decomposition to 1/8 and 1/10 of its initial concentration are T1/8 and T1/10 respectively. In this particular value. Okay. Have a look at this particular equation. See. For example, the reaction is nothing. It is A gives B, whose rate constant is K, and the reaction follows the first order kinetics. Now, dear students, at time T is equal to 0. The initial concentration of reactant is A0. This has to be 0. Perfect. Now, I'm defining two times. The first time is at T is equal to T1/8. This is the time at which the concentration of the reactant reaches to 1/8 of its initial value. So it's going to be A0/8. So at time T is equal to T1/8, the concentration of reactant left is equal to A0 divided by 8. Right? Similarly, at time T is equal to T1/10, the concentration of the reactant reaches to 1/10 of its initial value. So the concentration of reactant left is going to be A0/10. So this is the concentration of reactant left at time T is equal to T1/10. Right? So basically, what did I get? I got two conditions. At time T is equal to T1/8, this is the concentration of reactant left in the container. And similarly, at time T is equal to T1/10, this is the concentration of reactant left in the container. Oh, how many conditions do I have? I've got two conditions. I got two conditions basically. Yeah? I got two conditions basically. Now, my dear students, I'll be using these conditions in the integrate rate equation. Let's see what do we get. Let's see what do we get. If you remember, already I have given you one expression. T is equal to 0.303 divided by K. It's going to be log of A0 divided by AT. Do you remember this particular expression? Do you remember this particular expression? It is valid for the first order reactions. Now, in this expression, my dear students, I'm going to introduce these two conditions. Introducing first condition in this expression, instead of T, you'll be writing T1/8 is equal to 2.303 divided by K. It is log of A0 divided by, what is AT value here? AT value is A0/8. Perfect. So can I say A0 not cancel? 8 comes up. 8 can be written as 2 raised power 3. 8 can be written as 2 raised power 3 here. 2 raised power 3. It can be also mentioned as log of m raised power n, n log m. So 3 comes to the front, then it's going to be log 2. So 3 comes to the front, then it's going to be log 2. 3 comes to the front, log 2. Log 2 is nothing, that is 0.3. Correct? So this one equation which I got. Now, if I introduce second condition in the given equation, so instead of T, I'll be writing T1/10. T1/10 is equal to 2.303 divided by K. It's going to be log of A0 divided by, what is AT? AT is A0/10. AT is A0/10. A0 don't cancel, 10 comes up. Log of 10 is 1, right? Log of 10 is 1. So this term is completely gone. So I got T1 eighth, I got T1 tenth. What exactly I'm supposed to calculate? I'm supposed to get the value of T1 by 8 divided by T1 by 10 multiplied by 10. This value I need to get. Tell me what is the value of T1 by 8? T1 by 8 is 2.303 divided by K. This will be 0.9, right? Whole divided by. What is the value of T1 tenth? It is 2.303 divided by K. Multiplied by what? Multiplied by 10. So this term is gone. 0.9 multiplied by 10, value comes out being 9. So 9 is going to be the answer of this question. Yeah? Is this clear to everyone? Is this absolutely clear to everyone? Quickly. Quickly, guys. One more question which we have on the screen. Let's give it a try. My dear students, as per this particular question, for a first order reaction, choose the correct value of half-life. Okay. We are supposed to get the half-life. We are supposed to get the half-life. The graph is given to me. Log of 80 versus T. Log of 80 versus T. This particular graph, the straight line with a negative slope, it is valid for which reaction? Zero order or first order? It is valid for first order, right? So, okay, it's mentioned in the question only. The reaction is first order, whose graph is given. The reaction is first order, whose graph is given. What do I need to calculate? I need to get the half-life. What is half-life all about? What is half-life all about? Half-life of the first order reaction is nothing, that is 0.693 divided by K. So basically, in order to get the half-life of the reaction, what do I need? I need the rate constant. Where do I get the rate constant? From this particular graph. I'm given with the graph log T versus T. And you know, log T versus T, its slope, few minutes back only I've told you. Its slope will be equal to minus K upon 2.303. Right? What is slope? Slope is tan of theta. What is theta? Theta is the angle which this straight line makes with the positive x-axis in the anti-clockwise direction. So this is the theta, right? So slope is tan of theta. Tan of what? Tan of theta, tan of 135, which is minus K upon 2.303. Now, my dear students, tan of 135, how much is that? That's minus 1. So minus 1 is equal to minus K upon 2.303. Or I can say K is equal to 2.303. Since time is given in minutes, so K units are going to be simply minute inverse, right? So K you got. Why did I get this K? Because I had to calculate half-life, right? So I would say half-life of this reaction is equal to 0.693 upon K, which is 2.303, right? Perfect. And it's minute inverse in the denominator. So I would say T half will come out to be how much? It will come out to be 0.3 minutes, right? So half-life of this particular reaction, whose graph was given to us, it is simply equal to 0.3 minutes. I hope this is clear. I hope it's again clear to everyone. Yeah? Is it clear, people? Quickly. Is it clear to everyone? Let me know in the chats. Let me know in the chats. How many parameters, how many characteristics are we done with? We were, I think, done with 6 parameters, 6 characteristics of first order. Let's have a look on the 7th one. Let's have a look on the 7th one. Seventh one. The 7th parameter is calculation of the concentration. Calculation of the concentration of a reactant. Calculation of the concentration of reactant left after n half-lives. Well, there is one expression which I'm going to give you directly. Let's not derive that because that's going to be a wastage of time, nothing else. So I'll be giving you the expression, my dear students, and I'll show you how to utilize that expression. Yeah? Try to understand what exactly I'm going to talk about. Concentration of reactant left after n half-lives. Imagine that you have got a reaction A gives B. Imagine that you have got a reaction A gives B. I'm assuming it's following the first order kinetics. It is basically a first order reaction. It is basically a first order reaction, right? For example, just to make you understand. For example, half-life of the reaction is 10 minutes. Let's say half-life of this particular reaction. Let's assume that's 10 minutes, Okay, let's assume that's 10 minutes. If I write T is equal to 20 minutes, if I write T is equal to 20 minutes, can you let me know if half-life of this reaction is 10 minutes? Can you tell me how many half-lives this T is equal to 20 minutes will represent? See, half-life is equal to 10 minutes. So 20 minutes will represent how many half-lives? This 20 minutes, it will represent how many half-lives? It will represent 2 half-lives. Right? Simple. If I write T is equal to 30 minutes, so 30 minutes will represent how many half-lives? 30 minutes will represent simply 3 half-lives. Right? If I write T is equal to 100 minutes, 100 minutes will represent 10 half-lives. So first of all, how do we calculate the total number of half-lives? Total number of half-lives which I'm representing with n. Total number of half-lives I'm representing with n. It is always equal to total time T divided by T half. It will always give you the number of half-lives. It will always give you the number of what? It will always give you the number of half-lives, right? Okay. Now, I'm asking you to calculate the concentration of reactant left after n half-lives. How do we get it? I'm just going to give the expression. No need of derivation. AT is the concentration of reactant left after n half-lives is equal to A naught divided by 2 raised power n, where A naught is the initial concentration, right? And n stands for the number of half-lives. So this is one more expression which we'll frequently use in the question. But this particular expression, where do we use it? This particular expression is used to calculate the concentration of reactant left after n half-lives. Perfect. It has got the derivation as well, but again I'm telling you, no need of derivation. Remember the result, do the questions from this particular result, that's it. Let's try to see certain questions first, then you'll get to know where do we use this particular expression. This is the question. The question is, rate constant for the first order reaction is 1.386 minute inverse, right? So the units are minute inverse, that means the reaction must be first order, okay? Calculate the concentration of reactant left after 8 minutes. Calculate the concentration of reactant left after 8 minutes. So T value is equal to 8 minutes. We have to calculate the concentration of reactant left after 8 minutes. Okay. Now, first of all, as per the question, rate constant of the reaction, that's 1.386 minute inverse. My dear students, if rate constant of the reaction is equal to 1.386 minute inverse, can you let me know what will be the half-life of the reaction? Half-life will be equal to 0.693 divided by K, and K is nothing, that is 1.386. So the value is equal to 0.5, right? Minutes. So this is the half-life. This is the half-life. Why do I need the half-life? Because I have to calculate the concentration of reactant left after 8 minutes. So let me exactly see how many half-lives these 8 minutes are. How many half-lives these 8 minutes are. So number of half-lives is total time divided by T half. Total time is 8 minutes. T half is 0.5. The value comes out to be 16. So basically, as per the question, I'm supposed to calculate the concentration of reactant left after how many half-lives? After 16 half-lives. And already you know the concentration of reactant left after n half-lives. That's equal to A naught divided by 2 raised power n. So the answer of this particular equation is going to be A naught divided by 2 raised power 16. So this is the concentration of reactant left after 8 minutes, or you can say this is the concentration of reactant left after how many half-lives? After 16 half-lives, right? Is that clear, people? Let me know in the chats quickly. Quickly, people. Is it clear? Okay, by the way, before solving the other questions, let me tell you one important thing. From 25th August till 31st August, there will be no session on YouTube. There'll be no session on YouTube from 25th to 31st. So what we'll be doing in that week? No session, be it chemistry, be it biology, be it physics, right? There'll be no session on YouTube from 25th August to 31st August. In this particular week, all the classes will happen on Unacademy platform. And these classes which are going to happen in Unacademy platform, these are what we call as special classes. Well, you must be thinking whether these classes are free or not. Absolutely, these classes are free, absolutely free for all. You just have to download. You just have to download your Unacademy app in the mobile or laptop, wherever you're seeing it, right? Download the Unacademy app. I'll be sharing the link of all the special classes which I'll be taking, right? I'll be sharing it in my personal Telegram group, right? And I'm sure all of you are already added in that, okay? Well, I have planned some 3 to 4 sessions, 3 to 4 special classes in this particular week, right? And whatever chapters we have completed till now on YouTube, like we have completed almost all the physical chemistry, right? Every chapter, from every chapter, I'll be doing some 100 top-notch questions, basically. We'll start with the mole concept, top 100 questions of mole concept, so that it'll be the revision and problem practice too. Similarly, the other chapters too, right? My first session on this Unacademy platform, right? In the special classes, it will be on 26th. 26th August, I'll be taking the first special class, right? Similarly, 29th August, I'll be taking one more special class. Similarly, 31st August, I'll be taking one more special class. These are the 3 special classes which are planned, right? So I'll be doing some 100 questions in every session from the chapters which we have already covered. So that will be a problem practice as well as you'll remember the chapter properly. Is that cool? And tomorrow I'm going to take one special session at 10 p.m. on this channel in which I'm going to let you know the other things, the surprises which are going to be for all the NEET 2024 students as well. Yeah? Okay? But you have to join these sessions, my dear students, right? I'll share the link of the sessions in the Telegram. I hope you all are in my Telegram group, right? It is t.me/WASSIMSIRCHEM. Okay? Perfect. Surprise, you'll get to know tomorrow, not now. Surprise will be tomorrow. This particular week is going to be the problem practice week from the chapters which we have already covered on YouTube. Okay? Perfect. Look at this particular question. The question asks us, what amount of reactant for the first order reaction will be left after 3.5 minutes? We have to see the amount of reactant, the concentration of reactant left after 3.5 minutes. After 3.5 minutes. The graph is given to us. Ln 80 versus T graph. It is given to us. Why is it needed? Let's have a look. See guys. First of all, since I need to calculate the concentration of reactant left, 80. 2 minutes back only I told you 80 is nothing. That's A naught divided by 2 raised per n. A naught divided by 2 raised per n. What is n? N stands for number of half-lives, which is total time divided by T half. And what is total time? Total time is given to us as 3.5 minutes. So 3.5 divided by T half, right? What is T half all about? T half is nothing. That is the ln of 2 divided by K. Perfect. Ln of 2 divided by K. So basically, I need to calculate the concentration of reactant left after 3.5 minutes. So first of all, I'll see exactly how many half-lives these 3.5 minutes are. Are these 2 half-lives, 3 half-lives, 4 half-lives? Accordingly, I'll use this particular result, right? And in order to get the number of half-lives, I should know the half-life of the reaction. In order to get the half-life, I should know the rate constant of the reaction. And rate constant of the reaction, I'll get to know from this curve. Ln 80 versus T. Do you remember what is the slope of this particular curve? Slope of this particular curve, ln 80 versus T curve. This is something which we have discussed already, right? It's minus K, correct? So my dear students, slope is what? Tan of theta. And which is theta? Which is theta here? Theta is the angle which the curve makes with the positive x-axis in the anti-clockwise direction. This is theta. Now, if this is 45, this is 90, this is 45, so this has to be 135. So tan of 135. is -1. So -1 is equal to minus k. So k value is equal to 1 and it's going to be minute inverse. So we got the value of k. We got the value of k. K value is equal to -1, right? Sorry, k value is equal to 1. Ln of 2, we have to take as 0.7, 0.7 divided by 1. So this is the half-life. If this is the half-life, then this has to be 3.5 divided by 0.7. So number of half-lives came out to be 5. So indirectly, we have to calculate the concentration of reactant left after 5 half-lives, which is just going to be A naught divided by 2 raised power 5 molar. This is the concentration of reactant left after 5 half-lives, after 3.5 minutes. That's something which I was supposed to calculate, right? Let me know in the chats if all these things make sense to you, if they are clear to everyone. Quickly, people. Perfect, guys. Perfect. Okay. There is our one more Telegram channel. Just a second, guys. My wire is getting stuck. Okay. This is t.me/Unacademy NEET English. Unacademy NEET English. This is our official Telegram group, right? You can join this as well. I'll be sharing the link of this special class in this Telegram group as well, right? And one more is there. Again, I'm telling you, t.me/WSSIMSIRCHEM, right? That's mine. Any of the two you can join and get benefited. Okay, so I hope till here every single thing seems clear, right? Now, guys, there is one more type of the question. There is one more type of the characteristic feature which you have to remember. That is going to be the 9th characteristic feature. Is it 9th or 8th? I believe it's 9th, right? 9th or 8th, whatever it is. So one more characteristic feature, one more type of the question which can be asked basically from the first order reactions. When the concentration of reactants at 2 different times are given, what it means exactly. Try to understand. I'm again not going to derive the result. I'll be giving you the result and I'll show you how to utilize that result. You are given with a first order reaction A gives B, for example, whose rate constant is how much? Whose rate constant is K. It's a first order reaction. Assume that. Now, for example, at time t is equal to 0, the initial concentration of reactant is A naught. Let's say at time t1. Let's say at time t1. At time t1, the concentration of reactant left is 81. And let's assume when the concentration of reactant left is 81, at that point of the time, the rate of the reaction, that's R1, for example. Similarly, at time t2, the concentration of reactant left, that is 82. And let's assume that the rate of the reaction at this particular point is R2. It is R2. Be careful with these terminologies. At time t1, the concentration of reactant left is 81 and the rate of the reaction is R1. At time t2, the concentration of reactant left is 82 and the rate of reaction is R2, right? I am, for example, asking you, how much time will it take? How much time will it take for the concentration of reactant to reduce from 81 to 82? That means I'm asking you this particular time interval, which is t2 minus t1. I'm asking you this particular time interval, which is t2 minus t1, right? I hope you got it, what I said. I hope you got what I said. I'm asking you to calculate the time taken in which the concentration of reactant changes from 81 to 82. That means this particular time interval I'm asking you, t2 minus t1. How do we get this particular time interval? There is one result which I'm going to give you directly. You'll be remembering that from now onwards for all the first order reactions. The expression is K is equal to 2.303 divided by, it is t2 minus t1. Then we have log of 81 divided by 82. This is one expression, or you can write it like this as well. 2.303 divided by t2 minus t1. It's going to be log of rate of reaction at time t1 divided by rate of reaction at time t2. So this is the expression which I want all of you to remember, my dear students. Yeah? No classes on YouTube from 21st August to 31st August. They already know it. I have told them. There will be no classes. All the class will happen on the platform in the form of special classes, right? Okay, guys. Now let's exactly see how this particular expression is used in the questions. What kind of questions will be asked? See, for example, this is one simple question which I'm giving you, right? The rate of the first order reaction is 0.04 moles per liter per second at 10 minutes and 0.03 moles per liter per second at 20 minutes after initiation. Find the half-life of the reaction. The equation is like this. The reaction is like this. A gives B, whose rate constant is, for example, K, and it's following the first order kinetics. Let's assume that at time t is equal to 0, the concentration of reactant is A0. Let's assume that at time t1, the concentration of reactant is, just a second. Let's assume that at time t1, which is equal to 10 minutes. At time t1, which is equal to 10 minutes, the concentration of reactant left, that is AT1, and at the same time, the rate of the reaction, which I'm representing with R1, that's given to me as 0.04 moles liter inverse second inverse. There's something which is given to me. Similarly, at 20 minutes, it's mentioned that at 20 minutes, let's assume that concentration of reactant left is AT2 and rate of the reaction at this particular point of time, it is given to me as 0.03 moles liter inverse second inverse. What are we supposed to calculate? We are supposed to calculate half-life of the reaction. How do we calculate half-life of the first order reaction? It is 0.693 divided by K. So basically, we have to get the value of K. And how do you get the value of K here? Few minutes back only I told you, K is equal to 2.303 divided by T2 minus T1. It is the log of R1 divided by R2. I gave you this expression, right? Perfect. Two rates of reactions at two different times are given to us. So of course, I'll be using this expression, right, to get the value of K. So K has to be equal to, it will be 2.303 divided by T2 minus T1 will be 10. Then it's going to be log of R1 by R2. R1 by R2, which comes out to be 4 by 3. So log of 4 by 3 is basically log of 4 minus log of 3. Log of 4, already you know that's 0.6. Log of 3, you know that's 0.47. Put it here, get the value of rate constant. Once you get the right value of rate constant, put it here and get the half-life. This is the general procedure, right? General procedure of solving this question. No need to think a lot about this, right? One more question. In what time will the molar ratio of ethylene to cyclobutane be 1? In what time will the molar ratio of ethylene to cyclobutane be 1? What it means exactly? Have a look. First of all, the reaction is C4H8 gives 2 times C2H4. He's asking you, in what time will the molar ratio of ethylene to cyclobutane be 1? Let's assume that at time t is equal to 0. The moles of reactants are, for example, A. A represents the initial moles of reactant. This is, for example, 0, right? Now, for example, at time t, let's assume that out of A moles of reactant, X moles got converted into products. So I'll be left with A minus X moles of reactant. Now use a stoichiometry. 1 mole of reactant gives 2 moles of product. So X moles are giving me 2X moles of product, right? So I assume the time t. At time t, the concentration of reactant left is A minus X. The concentration of product formed is 2X. Concentration or moles. Both are, I'm considering, same over here, right? What do we have to calculate? At what time will the molar ratio of reactant to that of product? At what time will the molar ratio of product to that of reactant is equal to 1? So I'm assuming this is the time at which the ratio of the moles of product to that of reactant, that is equal to 1. So I'm assuming this is the time t at which 2x divided by A minus X is equal to 1, right? So from this particular result, I can say 2x is equal to A minus X, right? Or you can say X is equal to A divided by 3. X is equal to A by 3. Perfect. What do I need to calculate? I need to calculate this time. I need to calculate this time at which the ratio of the moles of products and reactants is equal to 1. Now what I'll be doing? Just use the integrate equation. We know T is equal to 2.303 divided by K. It is the log of A naught divided by AT. This is the integrated equation. Now, my dear students, T we have to calculate. T is this time which we have to calculate, right? It's equal to 2.303 divided by K value. What is K value? Given to me as per the equation, 2 into 10 raised power minus 4 log of A naught means initial moles here, which is A. AT means the moles of reactants left at time T, which is A minus X. So A minus A by 3, which comes out to be 2A by 3. So A cancelled, 3 comes up. It is log of 3 by 2, which makes it log of 3 minus log of 2. Log of 3 minus log of 2, right? So this term approximately cancels out. 10 raised power minus 4 comes up, becomes 10 raised power 4. Log of 3 is 0.47. Log of 2 is 0.3. The value here comes out to be how much? It comes out to be 1700 seconds. So my dear students, it will take 1700 seconds for the ratio of moles of product to that of reactant to be 1, right? This is something which I was supposed to calculate. I hope you got to know how to deal with this question, right? I hope you got to know how to deal with this particular question. This was one more good question which I would say, right, that was given to us. Okay, one more question is there, but this will be the homework question. You'll do it on your own. There is one trick here in this question, guys. There is one trick here, right? Do not just go with the flow. There's a trick here in the question. There's a trick here in the question. You might have to use the equation P1 by P2 is equal to N1 by N2 as well, which we have studied in gaseous state. That is one more equation which you have to use in this question. Give it a try. I want you guys to use your brain at least, because if I solve all the questions, it won't make a sense first of all. Yeah. So you have to use the brain as well. So you have to give it a try after the end of the session. If you are unable to solve it, do let me know on my Telegram. I'll show you exactly how to deal with this question. Perfect. So this was your first order reactions. Now our next topic is going to be gaseous first order reactions. But before that, one more characteristic feature which I would want you to know so that you can solve the questions in lesser time. See, that is the 9th feature of the first order reaction. 9th characteristic feature of the first order reaction. Try to understand. For example, I'm given with a reaction A gives B. Let's say I'm given with a reaction A gives B. Okay. Now, my dear students, try to understand what I'm going to say. This is the table which I'm getting, right? This is the table, for example. Here I'm mentioning time. Here I'm mentioning concentration of reactant. Concentration of reactant or pressure of reactant, for example. Now, my dear students, at time T1, let's assume the concentration of reactant was A1. At time T2, let's assume the concentration of reactant was A2. At time T3, let's assume the concentration of reactant is A3. At time T4, let's assume the concentration of reactant is A4, right? For example, in the same time interval. What does that mean? What does same time interval mean? Same time interval means that T2 minus T1 is equal to T3 minus T2, which is equal to T4 minus T3, right? That means I'm talking about this time interval. Time interval everywhere is same. The time interval from T1 to T2 is same as that of T2 to T3 is same as that of T3 to T4. If, my dear students, in the same time interval, if in the same time interval, A2 divided by A1 value comes out to be same as that of A3 divided by A2, which comes out to be same as that of A4 divided by A3. What does it mean? It means that these concentrations at different times, they have got same common ratio. They have got same common ratio. What does that mean? That means the concentrations of reactants, they are forming, geometric progression. Whenever you see this kind of the scenario, in the same time interval, if the common ratio of the concentrations comes out to be same, that means if in the same time interval, the concentrations of reactants, they are forming the geometric progression, remember at that point of the time, the reaction which you have, it will be automatically following the first order kinetics. It is going to be a first order reaction. Where in case of zero order, they used to form arithmetic progression. Here they are not from the arithmetic progression. They are forming the geometric progression, right? Right, people? Is it clear to everyone? Is it clear to everyone? Okay, guys. So let's take a break till here. Let's take a break. And the time right now is 7:35. Let's take a half an hour break so that we'll have a proper rest and then we'll come back. Okay. So session resumes at perfect. Because I don't want myself to be tired, nor I want you to be tired. Right? Let's have some tea or something. Perfect. So you guys carry on till then. I'm giving you half an hour break. That's huge. First of all, I'll see you all at 8:05 with a new topic that's going to be kinetics of the first order gaseous phase reactions. Till then, you take care. Right? Okay, see you at 8:05. But I want everyone to be back, guys. Okay? Be back. Be back. It's going to be fun. Is everyone back? Is everyone back? Is everyone back? Guys, can you all hear me? Am I again perfectly audible, visible to everyone? Let me know in the chats quickly. Quickly, people, quickly in the chats if all of you can hear me again. Quickly, let me know in the chats again if all of you can hear me. Yes, Meghna, yes. Perfect, guys. So, till now we are done with the first order reactions, right? The general first order reactions, their integrated rate constants, half-life, completion time, degree of dissociation, and the other parameters too. Now, my dear students, it's time for the kinetics of a gaseous first order reactions, right? This is again one important topic, and it's simple at the same time, right? So again, we'll be starting from the basics only so that you can understand this particular topic in detail with a proper understanding, okay? So first of all, imagine that you have got a reaction A gas, it gives B gas plus C gas. Let's assume this is a reaction. Imagine that it's a balanced chemical equation in which the stoichiometric coefficients are 1, 1, and 1, right? First of all, is the state of all the reactants and products same? Absolutely. The state of all the reactants and products is same. So this particular reaction, in which the state of all the reactants products is kept same, you call this particular reaction as the homogeneous reaction, right? And at the same time, the state of all the reactants products is gas in particular. So I'll be calling this particular reaction as homogeneous gaseous phase reaction. So it is the example of homogeneous gaseous phase reaction. My dear students, I'm assuming the order of this particular reaction as 1. I'm assuming the order of this particular reaction 1. If the order of this particular reaction is 1, then only I'll be calling this particular reaction as homogeneous first order gaseous phase reaction. So I'm assuming this particular reaction is the homogeneous first order gaseous phase reaction, right? Now try to understand what exactly I'm going to say. Something very important. My dear students, first of all, this particular reaction, it will be taking place in some container which is closed. For example, I've got a container which is closed on all the sides, and in that particular container, this reaction has to take place, correct? I am assuming this particular reaction taking place at constant volume and temperature. I'm assuming this particular reaction taking place at constant volume and temperature. Now, my dear students, if you use the ideal gas equation says PV is equal to nRT. I'm keeping volume and temperature constant. R is already constant, so I can say pressure is directly proportional to moles. What does that mean? That means if moles decrease, pressure will decrease. If moles increase, pressure will increase, right? And my dear students, if moles decreases, pressure will be decreasing. That means the proportion in which the moles will decrease, in the same proportion, pressure will also decrease. The proportion in which moles will increase, in the same proportion, pressure will also increase. What does that mean? Try to understand what exactly I'm going to say. My dear students, let's assume at time t is equal to 0. At time t is equal to 0, there will be only reactant present in the container, right? Because at time t is equal to 0, I'm assuming the reaction has not started yet. If the reaction has not started, there'll be no product formation. That means in the container, there'll be only reactant, right? So at time t is equal to 0, we'll be only having gas A in the container, right? There'll be only one gas in the container at time t is equal to 0. That is gas A, right? So whatever will be the pressure of the container at time t is equal to 0, that pressure will be entirely due to A. Let's call that as P naught. P naught is the pressure at time t is equal to 0, which is particularly due to A. Since B and C is not formed yet, so pressure due to B and C, that is absolutely 0, right? Now, my dear students, what will happen when the reaction starts? When the reaction starts, the number of moles of reactant will keep on decreasing. Its number of moles of A will keep on decreasing. That means pressure due to A will also keep on decreasing, right? Since if moles of A decreases, pressure due to A, that also decreases. And the proportion in which moles of A will decrease, in the same proportion, pressure of A will also decrease. Now, my dear students, the treatment which we used to do with the moles, the same treatment we are going to do with the pressure as well. So let me assume at time t, the pressure due to A, it is going to be P naught minus X, because the pressure due to A has reduced by how much amount? By X amount, right? Now, imagine as if this is not pressure. Imagine it's moles. Now, 1 mole of A gives 1 mole of B. So X moles of A will give me X moles of B. Similarly, 1 mole of A gives 1 mole of C. X moles of A gives X moles of C. But is this X actually moles? No, it's pressure. So this P naught minus X, this is the pressure due to A. This is the pressure due to B. This is the pressure due to C. Right? Try to understand. At time t is equal to 0, there was only one gas in the container. At time t, there are 3 gases in the container. Right? There are some moles of A which will be there in the container. Some moles of B and C which would have got formed. So if I ask you whether at time t, is there only one gas or we have got a mixture of gas at time t? I would say at time t, we have got a mixture of gas. At time t, we have got a mixture of gas, right? My dear students, if I ask you, just a second, what just happened? Okay. So if I ask you, what will be the total pressure of the mixture at time t, which I'm representing with PT? PT represents the total pressure of the mixture at time t. Since at time t, there are 3 gases in the container. Gas A, there are some moles of gas B which have got formed, some moles of gas C. So there are 3 gases in the container. So the total pressure of the mixture at time t, that is absolutely going to be P naught minus X plus this X plus this X. Right? So I must say this X and X got cancelled. So I would say PT is equal to P naught plus X. Right? From this particular expression, can I get the X value? X value is equal to PT minus P naught. So first of all, I got the value of X. Right? Now people understand. Since it is the first order reaction, it is the first order gaseous phase reaction, right? Order of the reaction is 1. We know it. Order of the reaction is 1. A first order reaction never undergoes 100% completion. It takes infinite time to undergo 100% completion. So my dear students, at time t is equal to infinity, I would say 100% of the reaction would have got completed. So 100% of the reactant would have got converted into product, right? So will there be any reactant left in the container at t is equal to infinite? No, there is no reactant left in the container at t is equal to T infinity. So pressure due to reactant at t is equal to infinity will be 0. Now all the reactant has got converted into product at t is equal to infinity. So if I say 1 mole of A gives 1 mole of B, so from P naught, you will be getting P naught. Similarly, 1 mole gives 1 mole, from P naught, you will be getting P naught. Perfect. Now if I ask you, what is the total pressure of the mixture at infinity? Total pressure of the mixture at T is equal to infinite. It's going to be 0 plus P naught, which makes it 2 times P naught, right? So from this particular expression, you can say P naught is nothing. It is just P infinite divided by 2. So what is this P naught? Basically, I got the value of P naught exactly from here, right? I got the value of P naught from here, which came out to be P infinite by 2. Now you must be thinking, why did I do it? Why did I get the value of X? Why did I get the value of P naught? You have to remember this procedure, guys, first of all. You have to remember this procedure. Perfect. After writing all this stuff, now I'm going to do one thing. First, I'm going to write the rate constant. I'm going to write the rate constant in terms of, I'm going to write the rate constant in terms of PT and P naught. Let's try to write the rate constant expression in terms of PT and P naught. How do you write the expression for rate constant for the first order reaction? You know it. You know K is equal to 2.303 divided by T. It used to be log of A naught divided by AT, right? It used to be log of A naught divided by AT. But for this particular reaction, for this homogeneous gaseous phase reaction, if you want to write the rate constant, in terms of P naught and PT, how you are going to write it? You will be writing K is equal to 2.303 divided by T. It is log of, what is A naught? A naught is initial concentration of reactant. But here, I won't be using the term initial concentration. I'll be using the initial pressure of reactant. And initial pressure of reactant is P naught. So instead of A naught, I wrote P naught. What was this AT? AT used to be the concentration of reactant left at time T. The concentration of reactant left at time T. But here, AT won't be the concentration of reactant left at time T. It is going to be the pressure of reactant left at time T, right? Which is P naught minus X. So this is P naught minus X, right? So K value here will come out to be 2.303 divided by T. It's going to be log of P naught divided by P naught minus X. X value already we have calculated, that is PT minus P naught. So this is PT minus P naught. So my dear students, I got one important expression. Well, you are not supposed to remember this expression, but you should know exactly how to make this expression. That is important because question is directly asked. You will have to make this particular expression. So it will come out to be 2 times P naught minus PT here, right? So this is the expression of rate constant for the first order gaseous phase reaction in terms of what? In terms of P naught and PT. Again, I'm telling you, you're not supposed to remember this expression. You should be able to make this expression, right? Because if you change the stoichiometry, then absolutely on changing the stoichiometry, the expression will change. Now guys, one more question is asked. What is that? That is the rate constant in terms of rate constant value in terms of PT and P infinite. Rate constant in terms of PT and P infinite. Now you can easily check it out. Since already I have told you P naught is equal to P infinite by 2. Already I have told you P naught is equal to P infinite by 2. So wherever in this expression you are seeing P naught, just replace the value of P naught by P infinite by 2. So what do I get? I'll be getting K is equal to 0.303 divided by T. It is the log of. Instead of P naught, you'll be writing P infinite divided by 2. Whole divided by. It is 2 times. Instead of P naught, again P infinite by 2 minus PT. So K automatically will come out to be 2.303 divided by T. It is the log of. See, this 2 gets cancelled. So P infinite divided by 2 times P infinite minus PT. So this is the expression of rate constant in terms of PT and P infinite. These questions are directly asked you in the examination. And all these expressions are basically valid for this particular reaction, which is A gas gives B gas plus C gas. I hope you exactly got to know the procedure of getting the rate constant, right? Now I'll be giving you one more example, and with that example, I'm damn sure it will be absolutely clear to you. Let me know in the chats if all the things are clear. Let me know in the chats if all the things are clear, whatever I've told you. Quickly, people, everyone. Everyone. Guys, am I audible, visible to you properly? Okay, yes, perfect. All right, let me give you one more example. So basically, this was your expression which we got. What was P naught? P naught was the initial total pressure. PT is the total pressure at time T. P infinite is total pressure at the completion of the reaction. Okay, let me see one more example so that you'll understand it properly. See guys, you are given with a reaction. You have to get the rate constant in terms of P naught PT. That's the first question. The second question is get the rate constant in terms of PT and P infinite. Sorry, this is the second question is PT and P infinite. Right? These are the two questions basically. Now you should be able to form the rate constant expression. Right? And I'm sure you can easily do that. See what exactly you'll be doing. Let me write the reaction again. So 2 times A gas, it gives 3 times B gas plus 4 times C gas. It is the homogeneous gaseous phase reaction which will be carried out in some container which is closed on all the sides. At time t is equal to 0, there will be only a reactant in the container. So there is only one gas in the container at time t is equal to 0. So whatever is the pressure of the system at time t is equal to 0, that is due to A, which I'm representing with P naught. So pressure due to B and pressure due to C at time t is equal to 0, that's 0, right? Because the reaction has not started yet. Product formation has not been done yet, right? So there is only one gas in the container at time t is equal to 0, that is A. So whatever is the total pressure at time t is equal to 0, that is due to A, which is equal to P naught, right? Now, how we are going to treat the pressure? We are going to treat the pressure in the similar way as we used to treat the moles, right? Now, my dear students, at time t, pressure due to A has to be P naught minus X, right? Now, use the stoichiometry. 2 moles are giving us 3 moles. 1 mole gives 3 by 2 moles of B. So, X moles are going to give us 3 by 2 multiplied by X moles of B. So, my dear students, this 3 by 2x, what is it actually? Actually, it is the pressure due to B at time t. Similarly, what is the pressure due to C at time t? Use the stoichiometry. 2 moles gives 4 moles. So 1 mole gives 2 moles. X are going to give me 2x moles. So what is this 2x basically? 2x is the pressure due to C at time t. Now, if I ask you one thing, at time t, how many gases will be there in the container? There will be 3 gases in the container. There are some moles of A which are left in the container, some moles of B which have got formed, some moles of C which have got formed. So at time t, you will find 3 gases in the container, right? So at time t, you are finding basically a mixture of gas. If I ask you total pressure of the mixture of gas at time t, total pressure of the gaseous mixture at time t, how much it's going to be? It's going to be P naught minus X plus 3 by 2x plus 2x, right? Perfect. If you take P naught on the other side, it's going to be Pt minus P naught is equal to. Now take 2 as LCM. So this will be minus 2x plus 3x plus 4x, right? So you'll be getting Pt minus P naught is equal to. This will be x plus 4x, which makes it 5x. So 5x divided by 2. From this particular expression, you can get the value of x. X value will be equal to 2 divided by 5 times Pt minus P naught. This is our first step always to get the value of x, right? So what did we get? We got the value of x from here. We got the value of x from here, right? Now, my dear students, if I continue, if I write t is equal to infinity, right? First order reaction, it takes infinite time to complete. So t is equal to infinity. Pressure due to A will be 0. Now we use the stoichiometry. 2 moles are giving 3 moles. 1 mole gives 3 by 2 moles. From P naught, you get 3 by 2 P naught. This is the pressure due to B at t is equal to infinity. 2 moles gives 4 moles. 1 mole gives 2 moles. So P naught is going to give us 2 times P naught. This is the pressure due to C at infinity. So if I ask you, what about the total pressure of the system at infinity? Total pressure at infinite time will be equal to. Total pressure at infinite time will be equal to P divided by 2 P naught plus 2 times P naught, right? So P infinite is just going to be 3 P naught plus 4 P naught makes it 7 P naught divided by 2. From this particular expression, you can get the value of P naught, which is going to be 2 times P infinite divided by 7. So you got P naught in terms of P infinite as well. So all the things are done. Now we just have to write the expression of rate constant. First in terms of P naught Pt and second in terms of what? Pt P infinite. So my dear students, first of all, I'll be writing the rate constant. Rate constant in terms of what? Rate constant in terms of P naught and Pt. Rate constant in terms of P naught and Pt. How do I get this rate constant expression? It is simple. K is equal to 2.303 divided by T log of. It used to be A naught by AT. What was A naught? Initial concentration of reactant. But here I won't be using initial concentration of reactant. I'll be using I'll be using initial pressure of reactant, that is P naught, right? So it's initial pressure of reactant divided by. It used to be AT in the denominator. Concentration of reactant at left T. Concentration of reactant left at time T. But here I'll be using pressure of reactant left at time T, which is P naught minus 6. Already we have got the X value, if you remember. So it is 2.303 divided by T. It is a log of P naught divided by P naught minus X value. I believe I've already calculated 2 by 5 PT minus P naught. So this is 2 divided by 5 PT minus P naught. Correct? Well, you can further solve it a bit, cross multiple this a bit and get the exact value of K. Well, the value of K which you will get from here, it is 2.303 divided by T. Then it's going to be log of, this will be P naught divided by. It is 5 P naught minus 2 times PT plus 2 times P naught, and in the numerator you'll write 5. After doing the calculation, that's all, right? So final expression of K has to be 2.303 divided by T. It is going to be log of 5 times P naught divided by 7 times P naught minus 2 times PT. Perfect. This is something which you were supposed to calculate. Expression of rate constant in terms of PT and P naught. So you got the expression of rate constant in terms of PT and P naught. I hope this is clear. Atomic structure will be done also. Just wait. After this chapter, maybe I'll start atomic structure. All right. What is the second part of the question? Second part of the question is calculate the rate constant in terms of PT and P infinite, right? Calculate the rate constant in terms of PT and P infinite. So what exactly you'll be doing in this question? Already we have got the relation between P naught and PT. You know, P naught is equal to 2 by 7 P infinite. P naught is equal to 2 divided by 7 P infinite. So what you have to do just is, in this expression, wherever you see P naught, instead of P naught, you have to write 2 by 7 P infinite. You'll be getting one more expression of K. That will be in terms of what? That will be in terms of PT and P infinite. That's it. So P naught value, you have to substitute here. You'll be getting the exact value of K in terms of PT and P infinite. I hope this is clear to everyone. Can you let me know quickly in the chats? Can you let me know quickly in the chats if this is clear to everyone? Quickly, people. Quickly, everyone. Yes? I hope you can solve these sort of questions. Let me know quickly in the chats if all of you can solve these sort of questions. Perfect. Let me give you one more question. You're given the reaction. Assuming ideal gas behavior, calculate the order of the reaction. There is some table that's given to me. A table is given to me. From this particular table, we have to see the order of the reaction first. Few minutes back only I told you a way to check the order of the reaction from the table, right? First of all, I want you guys to see, is the time interval same? 0 to 100. That means the time interval here is 100 minutes, right? Then from 100 to 200, again the time interval is 100 minutes, right? So the time interval is same, right? So the time interval is same. If the time interval is same, now check whether the pressure of reactant is X, right? Whether the pressure of reactant, whether it forms GP or AP. Say, if I divide 400 by 800, the value comes out to be 1 by 2. Then if I divide 200 by 400, the value again comes out to be 1 by 2. So is the common difference same or common ratio same? In the same time interval, is the common ratio of the pressure of reactant same or common difference? It is the common ratio which is same. And in the same time interval, if the common ratio of the concentration of reactants or the pressure of reactants, if it is same, we say these pressures, they form the geometric progression, and geometric progression is formed in case of what? In case of zero order or first order. It is formed in case of first order reactions. So first question is done, order of reaction is 1. So we got to know that the reaction is of first order. This is the first order reaction, right? Now we have to calculate T half and T 75%. T half and T 75%. But before that, let's try to calculate the rate constant first. Let's try to calculate the rate constant. How do we get the rate constant? See, at time t is equal to 0, pressure due to reactant, we know, right? At time t1, pressure due to reactant is 400. At time t2, pressure due to reactant is 200. Perfect. Now, my dear students, you can choose any time interval. Let's assume I'm choosing this time interval. I'm choosing this time interval, 0 to 100 minutes. So this I'll be calling as A0. This I'll be calling as AT. As simple as that. Or you can call it as initial pressure. This is the pressure of reactant at time t. Right? Nothing I'm doing. Nothing extra I'm doing. Use the expression. K is equal to 2.303 divided by T. Time interval is 100 seconds, which I'm choosing. Log of. No matter if you are given with the pressure of reactant or concentration of reactant, you'll use the same thing. You'll use the same procedure, right? So it was supposed to be A0, initial concentration of reactant, but here I'll be using initial pressure of reactant, which is 800 divided by it used to be 80, concentration of reactant left at time t, but here I'll be using the pressure of reactant left at time t. Perfect. This is time t is equal to 0, this is time t, right? So this has to be 400. Because I've chosen this time interval over here. I've chosen this time interval. I hope you're getting it. So K value from here, I'll be getting 2.303 divided by 100. It's going to be log of 2. And log of 2, you know, that's 0.3. So multiplied it with 0.3. Perfect. So you'll be getting K. Well, if I ask you whether this is the rate constant of the reaction or not, the units are minute inverse. Whether it is the rate constant of reaction or not, if I ask you, what do you think? Is it the rate constant of reaction? My dear students, see, the stoichiometry here is 2. The stoichiometry here is 2. If the stoichiometry is not 1, if the stoichiometry of reactant is not 1, then I should be calling this as rate constant of disappearance of X. I hope you remember in the last session I've told you. I'll be calling this as rate constant of disappearance of X. Now, you know, rate constant of disappearance of X has to be equal to rate constant of reaction multiplied by stoichiometric coefficient of X. So from here, you'll be getting rate constant of reaction as Kx divided by stoichiometric coefficient. So it is 0.606 divided by 100, right? And divided by stoichiometric coefficient of X. That is 2. So it has to be 200. Now it's going to be minute inverse. Now this is the rate constant of the reaction. This is now the rate constant of the reaction. Yeah? Now you got the rate constant of the reaction. So rate constant of the reaction you calculate it. Well, after getting the rate constant of the reaction, calculate T half. How do you calculate T half? T half is equal to 0.693 divided by K reaction. K reaction already you have calculated, right? Put it here, get the T half. Calculate T 75%. T 75% is 2 times the T half. 2 times the T half. T half you have calculated from here. So you can calculate T 75% too, right? Total pressure when Px is equal to 700. This should be your homework. You should be able to solve this one as well. Total pressure of the system when Px is equal to 700. It's again simple. It's again simple, guys. Is it clear? Is it clear to everyone? Say yes or no in the chats quickly. Okay, let me show you the total pressure also. Total pressure when Px is equal to 700. See, you're given the reaction 2x gas, it gives 3y gas plus 2z gas. Initially at time t is equal to 0. Pressure due to x is 800. So this is 0, this is 0. Now, let's say at time t, pressure due to x is 700. Pressure due to x is 700. So how much is reduced? 100 is reduced. So x value is 700. X value is 100. Now see, 2 moles are giving 3 moles. 1 mole gives 3 by 2. So 100 is going to give us 3 by 2 multiplied by 100. Right? Simple procedure. 2 moles are giving 2 moles. 1 mole gives 1. So 100 gives us 100. Perfect. So this is 250. 50 into 3 is 150. So I would say total pressure of the system at time t will be equal to 700, which is pressure due to x, plus pressure due to y, that is 150, and pressure due to z, that's 100. So this is 850 plus 100, that comes out to be 950 mm of Hg. So this is the total pressure of the mixture at time t, right? When the pressure of the reactant left is 700. This was 800, left is 700. So how much has got converted? 800 minus 700, that's 100. So 100 mm of Hg has got converted. Or you can treat them as moles. Imagine this is 800 moles initially. Now how much is left? 700 moles. That means 100 moles have got converted. Now, 2 moles gives 3 moles. 1 mole gives 3 by 2. 100 will give 3 by 2 into 100. You are going to treat pressure in the similar way as moles. No doubt you treated them like moles, but this is actually pressure. No doubt you treated it as moles, but this is actually pressure. So let me know once in the chat if this is clear. Let me know quickly, people. Will you be able to solve these sort of questions if they are asked? Will you be able to solve these sort of questions? Let me know once in the chat quickly. If these sort of questions are asked. Quickly, guys. Quickly. Yeah. I hope you got to know how to deal with these questions. Now, there is one more topic. That is kinetics of a first order parallel reaction. So first of all, what is a parallel reaction? What is the first order parallel reaction? What all expressions we have to remember? And how do we deal with these parallel first order reactions? Let's get to know. Try to understand. My dear students, the reaction in which a reactant is involved in more than one first order reaction. In which a reactant is involved in more than one first order reaction. What is meant by that? For example, you have got a reaction like this. A gives B, whose rate constant is K1. Let's assume this particular reaction is a first order reaction. Let's assume it's a first order reaction. At the same time, this A is getting converted into C, rate constant K2. I'm assuming, for example, this reaction also is the first order. So how many reactions actually these are? These are 2 reactions. This one is the first order reaction. Even this one is the first order reaction. And one reactant, it is common in both the reactions. One reactant is involved in more than one reaction. One common reactant that's involved in more than one reaction. Whenever you see such kind of the reaction, in which one particular reactant is involved in more than one first order reaction, you call this particular reaction as the parallel first order reaction. You call this as the parallel first order reaction. So what is the parallel first order reaction? In which a reactant is involved in more than one first order reactions like this. For example, A gives B, this is one first order reaction, and A gives C, one more first order reaction. Correct? Let's assume the rate constant of this is K1, this is K2. A gives B, it is first order. A gives C, it's also first order. Perfect. Now, guys, there are a few things which you need to remember. First of all, I'm not going to derive. I'll be giving the expressions, and I'll show you how to solve the questions with those expressions. My first expression here is going to be to calculate the average rate constant of the reaction. Average rate constant of this parallel first order reaction. Let me tell you, average rate constant of the parallel first order reaction is the sum of individual rate constant. It is the sum of individual rate constant. Average rate constant of this parallel first order reaction. It is the sum of individual rate constants. Point number 1, right? Point number 1. Point number 2, my dear students. If you ask me what is the integrated rate equation for this parallel first order reaction, it is same. What was the integrated rate equation for the general first order reaction? K is equal to 2.303 divided by T log of A naught divided by 80, right? But here instead of K, I won't be writing K. I'll be writing K1 plus K2. So K1 plus K2 is equal to 2.303 divided by T. It's going to be log of A naught divided by 80. This is going to be what? This is going to be called as the integrated rate equation. This is the integrated rate equation for the parallel first order reaction like this. A gives B, A gives C. Okay. Just in place of K, I wrote K1 plus K2. Now, for example, if there was one more reaction, A gives D, whose rate constant was K3, then I was supposed to write K1 plus K2 plus K3. Okay. If you remember one more equation I had given you in the first order, AT is equal to A naught e raised power minus KT. So instead of K, I'll be just writing K1 plus K2 multiplied by T, right? These are few equations which you are going to remember directly. No need for their derivation, right? Now, guys, is that it? That's not it. That's not it. Let me tell you a few more things. Try to understand. At time t is equal to 0, let me assume. At time t is equal to 0, let me assume. Let me assume at time t is equal to 0, the moles of reactants, for example, are A naught. Let's say A naught represents the moles of reactant at time t is equal to 0, right? Right? let's say A naught, it represents the moles of reactant at time t is equal to 0. Or you can say this is the concentration of reactant at time t is equal to 0. Because I'm assuming moles and concentration is same here. Right? I'm assuming moles and concentration is same here. So I'm assuming A naught represents the moles of reactant at time t is equal to 0. Or you can say A naught represents the concentration of reactant at time t is equal to 0. Correct? Now, my dear students, since the moles of reactant at time t is equal to 0 is A naught, moles of product at time t is equal to 0. That will be 0 also because the reaction has not started yet. Now, my dear students, what will happen with time? With time, the moles of reactants will keep on decreasing. With time, the moles of reactant will keep on decreasing. Let's say at time t, the moles of reactant left are 80. 80 represents the moles of reactant left at time t. And let me assume a term here, x. Let me define a term x here. Let's say x represents the number of moles or concentration of what? Of reactant. Of reactant, which got converted into products. Which gets converted into products. Which gets converted into products. Right? I'm assuming X are the moles of reactants which are getting converted into products. Now imagine how many moles you had? A naught. How many are we left with? 80. So A naught minus 80. A naught minus 80. A naught minus 80. Can I say A naught minus 80 gives me those moles of reactants which got converted into product? That's something which I call as X. So what is X? X is moles of reactant which got converted into product. Initially I start with A naught. I'm left with 80. So A naught minus 80. It gives me those moles of reactants which got converted into product. Right? Now, my dear students, there are few things which you need to know. What is that? See, at time t, there are some moles of reactant left. If I ask you what is product here in this reaction, I would say product in the reaction is B plus C. If you ask me what is product in the reaction, product in the reaction is B plus C. B plus C combinedly, I'm calling as product. B plus C combinedly, I'm calling as product. There are a lot of things which can be asked. There can be asked, calculate the moles of B which are formed at time t. Calculate the moles of B which are present in the container at time t. They can ask you, calculate the moles of C which are formed in the container at time t. How do we calculate moles of reactant left in the container at time t? How do we calculate moles of B which are formed at time t? How do I calculate moles of C which are formed? How do we do that? I'll be directly giving you one trick for their calculation. Try to understand what exactly I'm going to tell you. See guys, trick number one. Trick number one. For example, you have got the reaction like this. A gives B and at the same time A gives C. Its rate constant is K1, its rate constant is K2, right? At time t is equal to 0, the initial moles of reactants are A naught, right? At time t, the moles of reactants left are AT. Perfect. I'm defining a term X. What is X? X represents the number of moles. The number of moles or concentration of what? Of reactant. Of reactant. Converted into products. Converted into products. At time t. At time t. Try to understand. My dear students, if I ask you what are my products, if I ask you about the products, product at time t, product at time t, our product is going to be C and D. C and D combinedly I'm calling as product. C and D combinedly I'm calling as product. The first question that is asked, what is the percentage of B in the product? In the product. Calculate the percentage of B in the product. The product is B plus C basically, right? I'm asking you the percentage of B in the product. The percentage of B in the product. The product is C, the product, sorry, not B. Wait, C plus D. This is B plus C here, okay? Just, this is B plus C, right? B plus C combinedly I'm calling as product. The first question is asked, calculate the percentage of B in the product. Percentage of B in the product is simply written as K1 divided by K1 plus K2 multiplied by 100. This will be the first question which will be asked. Number one. Number two, percentage of C in the products. Percentage of C in the products. percentage of C in the products. It is just going to be equal to K2 divided by K1 plus K2 multiplied by 100. This will give you the percentage of C in the product, right? Now they can ask you, what about the moles of B which have got formed at time t? What about the moles of B which have got formed at time t? Now, how you are going to write it? Moles of B formed at time t. It is going to be equal. First, you will start with K1 divided by K1 plus K2. Now, 1 mole of A gives 1 mole of B. Therefore, X moles of A would have got X moles of B. So this particular term is going to give us the moles of B formed at time t. Similarly, what about the moles of C formed at time t? Moles of C formed at time t. Start with K2. You'll be writing K2 divided by K1 plus K2. Now, 1 mole of A gives 1 mole of C. Therefore, X moles of A are going to give us X moles of C. So I got the moles of C formed at time t as well. Now, my dear students, if you divide the two, moles of B formed at time t divided by moles of C formed at time t. So X cancelled, K1, K2 cancelled. So I'll be left with only K1 divided by K2, right? These are few expressions which you should be able to make on your own. Right? Few expressions, important ones. Why are they important? Because I'll show you the questions after few minutes, then you'll get to know about their importance. Right? Perfect. Now, guys, if, for example, by chance, they play with the stoichiometry, let's say they give you a question like this. N1A, it gives N2B, and at the same time, N1A gives N3C. Let's say they are giving it a question like this. The rate constant of the first reaction is K1, rate constant of this reaction is K2. Right? Again, I'm assuming certain things. At time t is equal to 0. The moles of reactant is A0. At time t, the moles of reactant left are 80. Right? These can be moles, they can be concentration, they can be called as concentration, they can be called as pressure. The choice is all yours. Right? Try to understand what exactly I'm going to do. I'm defining a term X. What is X? X you already know. What is X? X are basically the moles of reactant. X you can call either as moles or concentration or pressure. I'm right now calling it as moles. Moles of reactant getting converted into products. Moles of reactant getting converted into what? Into products. At what time? At time t. Now try to understand. The first question which will be asked. Calculate the percentage of, or leave the percentage aside. Tell me one thing. Moles of B which have got formed at time t. Moles of B or concentration of B formed at time t. You'll start with K1. Divided by K1 plus K2. Now, N1 moles are giving me N2 moles. N1 is giving me N2. So 1 mole gives me N2 divided by N1. So X moles of A are going to give me N2 divided by N1 multiplied by X. Right? Stoichiometry, that's it. Similarly, moles of C which have got formed at time t. Start with K2. So K2 divided by K1 plus K2. Now use the stoichiometry. N1 moles are giving N3 moles. So 1 mole gives N3 divided by N1. So X moles are going to give us N3 divided by N1 multiplied by X. Right? Okay. Now at the same time, if you divide them up, moles of B at time t divided by moles of C at time t, what I'll be getting? I'll be getting N2 times K1 divided by N3 times K2. Perfect. If they ask you, what is the percentage of B in the products? Calculate the percentage of B in the products. How you are going to do it? Percentage of B in the products. What is there in front of B? N2K1. So you'll write N2K1 divided by N2K1 plus N3K2 multiplied by 100. Right? This will give you the percentage of B in the products. If they ask you about the percentage of C in the products, at time t, for example. See, in front of C, what do you have? N3K2. So you'll write N3K2 divided by what? Divided by N2K1 plus N3K2 multiplied by what? Multiplied by 100. This will give you This will give you the percentage of C in the products, right? Perfect. So my dear students, these sort of questions can be asked, right? Well, I did not derive them. I'm just giving you the tricks to solve the questions. That's all. Let's try to see exactly what kind of questions can be asked out of these parallel first order reactions. Understand and see how we are going to deal with the questions. Try to understand, guys. Just a second. This is the first question. This is the first question. It is the simplest among all because the stoichiometry is 1:1:1. K1, K2 is also given to us. Calculate the percentage distribution of B and C in the products. My dear students, since the stoichiometry is 1:1:1, what about the percentage of B in the products? Percentage of B in the products. Since the stoichiometry is 1:1. When the stoichiometry is 1:1:1, when the stoichiometry is 1:1:1, 1:1:1, how do we get the percentage of B in the products? K1 divided by K1 plus K2 directly, right? So it is going to give B. It is going to be K1 divided by K1 plus K2 multiplied by 100. Correct? Now K1 value 0.693, right? K1 plus K2 0.693 plus 0.1386 multiplied by what? Multiplied by 100. Now 0.693 I'm writing as such. In the denominator, if I take 0.693 common, it's going to be 1 plus 2 multiplied by 100. So this term got cancelled. It is 1 divided by 3 into 100. The value comes out to be how much? The value comes out to be 33%, right? Right? 33%. So percentage of B in the products is coming out to be how much? It is coming out to be 33%. Yeah? Right, people? You got the percentage of B in the products. In the products, there won't be only B. There'll be C also, right? If they ask you about the percentage of C, which they have asked, percentage of C in the products. What about the percentage of C in the products? It's going to be 100 minus 33, which comes out to be 66%. This is the percentage of C in the products. Percentage of B, percentage of C in the products. Right? Is this clear to everyone? This is one type of the question. This is one type of the question. Right, people? Let's see the other types of question as well. Just a second. For example, look at this question. Look at this particular question. You should be able to solve this question. You see the question first, and then I'll see some other questions. Quickly. Can you give it a try? See guys, on starting with 2 moles of A, calculate the total moles after 75% completion. See, as per the question, the reaction is like this. A gives 2 times B, and at the same time, A gives 2 times C as well. Rate constant of this reaction is K1, rate constant of this reaction is K2. On starting with 2 moles of A, so initially at time t is equal to 0, how many moles of reactant we have? We are given with 2 moles of reactant. We are given with 2 moles of reactant, correct? 2 moles of reactant we have. So at time t is equal to 0, the moles of B and C formed, that will be absolutely 0, right? Because the reaction has not started yet. Now guys, calculate the total moles after 75% completion. What is meant by 75% completion? That means 75% of A has got converted. What is 75% of A? What is 75% of 2? 75 divided by 100 into 2. How much is that? 1.5 moles. So out of 2 moles of A, I would say 1.5 moles have got converted into products. So I'll be left with 2 minus 1.5. 2 minus 1.5 is 0.5. So these are the moles of A left in the container after 75% completion. If I ask you, what about X value? What is X? Moles of reactant which get converted into product. So I had 2 moles. Now 75% of 2 is getting converted into product, right? So that means 1.5 moles have got converted into product. So x value is equal to 1.5. So you got the value of x first of all, right? Now, at time t is equal to T75, the moles of reactant left in the container are 0.5. Now, there will be few moles of B and C also, which would have got formed at T75%. Absolutely. Now, calculate the moles of B at time t, which have got formed. Calculate the moles of B at 75% completion. See, how exactly? You know it. Start with K1 divided by K1 plus K2. Now use the stoichiometry. 1 mole of A gives 2 moles of B. If 1 mole of A gives 2 moles of B, that means x moles of A are going to give us 2x moles of B, right? Similarly, moles of C at time t. Moles of C at time t, it is going to be equal, start with K2. So it's K2 divided by K1 plus K2. K2 divided by K1 plus K2. Now, 1 mole gives 2 moles. So from x moles, you are going to get 2x. Perfect. Right, people? Now put the values and get the answer. See, K1 by K2 is 1 by 2. So this is 1 divided by 1 plus 2 multiplied by 2x. 2 into x is 2 into 1.5 is 3. So this is 3 divided by 3, which comes out to be 1. Right? Similarly, K2 value, this will be 2 divided by 1 plus 2. 2 into x is 3. So 3 2s are 6. 6 divided by 2 is 6 divided by 3 is, for example, 2. Right? So my dear students, if I ask you, when 75% reaction is completed, which all components are there in the container? There are some moles of A left in the container, some moles of B have got formed, and some moles of C have got formed. So how many total moles are there in the container when 75% of the reaction has got completed? Moles of reactant left, that's 0.5. Moles of B which have got formed, that's 1. Moles of C which have got formed, that's 2. So the final value comes out to be 3.5. I would say 3.5 moles will be there in the container in total when 75% of reaction would have got completed. Let me know in the chats if this is again clear to you. Is it clear? Is it clear, people, quickly? Yeah? Wonderful. All right, can you give this question a try? Can you solve this question? Initially, only A was taken at 8 atm. See guys, whatever treatment you do with moles, same treatment you do with concentration as well. Same treatment you do with pressure as well. Right? Same treatment, no change at all. Right? Assume moles is equal to concentration is equal to pressure. Same treatment everywhere. Look at this question. We are given the reaction A gives B, A gives C, and at the same time A gives D. K1, K2, K3 are given to us. K1, K2, K3 are given to us. Initially, only A was taken at 8 atm. So at time t is equal to 0. At time t is equal to 0. At time t is equal to 0, the pressure due to A, which I'm representing again with A naught, it's 8 atm. It is pressure due to A. So pressure due to C and D, pressure due to B, C and D, that will be 0 because the reaction has not started yet. Now, my dear students, the partial pressure of B after 100 seconds. The partial pressure of B after 100 seconds. So, first of all, you know when the reaction will start, the moles of A will keep on decreasing. The moles of B, C and D will start to increase, right? So, at 100 seconds, there will be some moles of A in the container. Moles of B, C and D will be there in the container. So, basically, at 100 seconds, there will be 4 gases in the container. Gas A, some moles of gas A left, some moles of gas B formed, gas C formed, gas D formed. So there are 4 gases in the container. So there will be a gaseous mixture present in the container at 100 seconds. Right? There will be a gaseous mixture present in the container at 100 seconds. Now you have to calculate. Let's assume that gaseous mixture will have some total pressure. The contribution made by gas B towards the total pressure of the gaseous mixture. The contribution of gas B towards the total pressure of the gaseous mixture is something which I call as partial pressure of B. And that partial pressure of B you have to calculate. And how exactly you'll be solving this. The partial pressure of B after 100 seconds. My dear students, first of all, K1, K2, K3 is given. Let's say I'm calculating average rate constant. What will be the average rate constant? This plus this plus this. If I take 10 raised power minus 3 common, right, it'll be 2 plus 3 is 5. 5 plus 1.93 is 6.93. So average rate constant came out to be 6.93. Average rate constant is coming out to be 6.93 into 10 raised power minus 3. Right? This is the average rate constant. If it is the average rate constant, can you calculate the average half-life? Average half-life is going to be 0.693 divided by K average. Simple. K average already you know. If you put the K average here, you got the answer as 100 seconds. Right? What is this 100 seconds? 100 seconds basically is the half-life of the reaction. 100 seconds is the half-life of the reaction. So basically what we identified that we have to calculate the partial pressure of B after 50% completion. We have to calculate partial pressure of B after 50% completion. It's a live lecture going on. It's not the recorded one. Okay. We have to calculate the partial pressure of B at half-life. So this 100 seconds is half-life. That means T 100 seconds means that 50% of reaction has got completed. When 50% of reaction got completed, that means 50% of reactant got converted into products. So tell me one thing. What will be the pressure of reactant left at T 50%? 8 by 2 is 4. So pressure of reactant left is 4 atm. Right? Because we are dealing with half-life right now. Correct, people? Correct? If I ask you what is the value of X? What is the value of X? X value used to be moles of reactant that got converted into product. But instead of moles, I'll be using pressure. So initially I had 8, now I'm left with 4. Therefore 4 atm has got converted. So X is 4 atm here. X is 4 atm. Now my dear students, try to understand. If I ask you what is the partial pressure of B at time T, that means T 50%, it's going to be equal to, first you'll write K1 divided by K1 plus K2 plus K3. This is the first step. Now, 1 mole of A gives 1 mole of B. Therefore, from X, you get X multiplied by X. Right? This is something which we need to calculate basically. So, partial pressure of B at time T is equal to 100 seconds is equal to K1 divided by K1 plus K2. K1 divided by K1 plus K2. Right? See, K1 value you have. K1 you have, K2 you have, K3 you have. Perfect? Right? Or let me just calculate it for you. K1 is nothing, that is 2 into 10 raised power minus 3 divided by it is going to be 6.93 into 10 raised power minus 3. The sum of them multiplied by X value is 4. So 10 power minus 3, 10 power minus 3 cancel. So it's going to be 8 divided by 6.93, which will be approximately 1.1 atm. So partial pressure of B, the contribution of B towards the total pressure of the mixture at 100 seconds will be exactly how much? It's going to be 1.1 atm. I hope this is clear to everyone. Yeah? Perfect, guys? I hope you can solve these sort of questions as well. Okay? One question I'm giving as the homework in this, or before giving you the homework question, one small topic is there which you need to know. Calculation of average half-life for the first order reaction. Calculate the average half-life for the first order reaction. See guys, for the first order parallel reaction basically, okay? Let's say you've got a parallel reaction like this, A gives B, A gives C, right? Its rate constant is K1, its rate constant is K2. Now first of all, average rate constant of this parallel reaction is going to be simply K1 plus K2. Perfect. It's going to be K1 plus K2. Now, my dear students, average rate constant. Can I write it as 0.693 divided by T half average? I can write it like this. Okay. What is K1? K1 can be written as 0.693 divided by partial half-life of the first reaction plus K2 can be written as 0.693 divided by partial half-life of the second reaction. So 0.693, 0.693 everywhere cancel. So you got to know 1 by average half-life will be equal to 1 divided by partial half-life of the first reaction plus 1 divided by partial half-life of the second reaction as well. Okay. So this is one more expression from which question can be asked. Right? This one more expression from which question can be asked. Okay. Right? From this particular expression, you can calculate the average half-life. Or my dear students, there can be one more expression. See, one more expression to calculate average half-life. The reaction, for example, is A gives B and A gives C. Rate constant of this reaction K1, this is K2. Now you know K average. That is nothing, that is K1 plus K2. Correct? Instead of K average, I can write 0.693 divided by average half-life, which is equal to K1 plus K2. So from this particular expression, you can also calculate average half-life. Average half-life of such reaction will be equal to 0.693 divided by K1 plus K2. Right? This is the average half-life of the reaction in terms of individual rate constant. So I'm writing it. This is basically the average half-life in terms of what? This is in terms of individual rate constants. Individual rate constants. And what was this one? What was this one? This is the average rate constant. Sorry, this is the average half-life in terms of partial half-lives. This is the average rate constant average half-life in terms of partial half-lives. Is this clear? Is this clear to everyone? You have to remove these two expressions as well, right? One question I'll be giving you as the homework. But before that, this is the expression which we have seen. Even this is the expression which we have seen. There was one question which I have kept as the homework for you, right? This was the question. Give it a try and you guys are going to let me know the answer of this question in the comment section afterwards. Okay, this is the question. This is your homework question. Average half-life is given. Percentage distribution of B in the products is given. Then the partial half-life of A. Simple question. It can be a bit lengthy, right? It can be a bit lengthy. Calculation must be involved here, right? But it's simple only. Yes, it's simple only. Calculation might be a bit tough, but it's doable. I mean, you should be able to do it after learning all the concepts which I told you. Okay. Okay, guys, is everything clear till here? See, average half-life is given. So you can calculate average rate constant from there, right? 0.693 divided by K. 0.693 divided by T half average, right? Then K average will be equal to K1 plus K2. Percentage of B in the products is given. That means 2 times K1 divided by 2 K1 plus 3 K2. 2 K1 divided by 2 K1 plus 3 K2 into 100 is given to us as 50. It's a simple question, guys, right? Order I have discussed in the second part of the kinetics chapter. Will you be able to do this question? Say yes or no in the charts once. Then only I'll move ahead quickly. I want everyone to say it quickly. Will you be able to solve this question? Okay, so we are done with the parallel first order reactions. Now, let me tell you one more important thing. From which question is asked frequently? From which question is asked frequently? That is order of the reaction. Order of the reaction from half-life. How do I calculate order of the reaction from the half-life? How do I calculate the order of reaction from the half-life? Okay. Try to understand what exactly I'm going to say. My dear students, for example, you have got a zero order reaction. For a zero order reaction, what is the expression to calculate half-life? A naught divided by 2k, right? For the first order reaction, half-life will be equal to 0.693 divided by k, right? For zero order reaction, for the first order reaction, correct? Now, can I say for the zero order reaction, half-life is directly proportional to initial concentration? For this first order reaction, half-life is independent of the concentration of reaction. For example, you have got nth order reaction. The reaction whose order is n. Can I simply say T half will be directly proportional to A raised power 1 minus n, where A is the initial concentration. For example, right? Check. If n value is, for example, 1, that means the reaction is first order. So 1 minus 1, 0. Anything raised power 0 is 1. So T half is independent. Absolutely correct. If n is 0, zero order. If n is 0, 1 minus 0 is 1. So T half is directly proportional to initial concentration. Absolutely. So this particular result is valid. It is valid, right? So from this particular expression, can't I write T half is equal to, it's a constant k, right? A raised power 1 minus n. Correct? Why am I giving you all this? There's a logic behind that. Just a second. People. Now, first of all, what I'll be doing from here, I'll just do one thing. I'll multiply this equation with log. It becomes log of T half will be equal to log of k plus 1 minus n log of A. This is the equation which I got. So basically, what did I do? I multiplied this equation with log. It became log of m into n, which is log of m plus log of n. Then it becomes n log m, right? This is the equation which I got. So first thing, for example, I'm making a graph. Let's say I have to make a graph. The graph is between log of T half versus log of initial concentration. Log of T half versus log of initial concentration. So this is y, this is x, this is m, this is c. Y is equal to mx plus c. It's going to be a straight line like this. What about the slope of this particular graph? Slope means m, which is 1 minus n, right? And what about the intercept of this particular curve? It is just going to be log of k. So my dear students, if by chance a graph like this will be given to us, log T half versus log initial concentration of reactant, slope of this particular curve is equal to 1 minus n. From there, if slope is given, let's say slope is given to us as 3. So yeah, slope is given us as 2 or whatever. So basically 1 minus n value is given. From there you can get the n value. You can get the order. Right? Yes, A is the initial moles or initial concentration of reactant. So from this particular graph, if the slope is given to us as per the equation, then easily n value, you can calculate the order of the reaction. Correct? Now, my dear students, if you look at this particular expression, where do you use this particular expression? T half is directly proportional to initial moles or initial concentration raised power 1 minus. Now, imagine you have got a reaction like this. A gives B. I have no idea what is the order of the reaction. Order of reaction is n, for example. It is n. Okay. For example, when the initial moles or initial concentration of reactant is A1, at that point, let's say half-life of the reaction is T half 1. When the initial moles or initial concentration of reactant is kept A2, at that time, let's assume half-life of the reaction is T half 2. Okay. Now we know T half is directly proportional to initial concentration of reactant raised power 1 minus n. So can I say T half of 1 divided by T half of 2 has to be equal to A1 divided by A2 whole raised power what? Whole raised power 1 minus n. So from this particular expression, you can also get a question. And frequently you have been getting the question in JEE Mains from this particular expression. Yeah? Right? Like you'll be given with 2 half-lives, 2 initial concentrations, you'll have to get the value of n. That's all. Will you be able to solve this? Quickly. Will you be able to solve this question? I just want to know in the chats. Will you be able to solve this question? Right, people? I cannot see your chats. Just a second. Just a second. All right. So I think you should be able to do this sort of equation on your own, right? If the initial concentrations are given, A1, A2 is given, T half 1, T half 2 is given. So I believe you can use this particular result and get the value of the order of the reaction, whatever is asked, right? And most of the times, the question which will be given to you, it will be given in the format of table. It will be given in the format of table like this. I'm just showing you. It will be given, I'm showing you the format of the question. It will be given like this. For example, T half and concentration of reactant, right? If the initial concentration of reactant is A1, at that time, half-life of the reaction will be given to us. Similarly, initial concentration of reactant when kept A2, half-life of the reaction will be given to us at that time also, right? So A1, A2 will be given, T half 1, T half 2 will be given. You have to put in this expression, compare and get the value of, solve, get the value of N. Perfect. So do remove this particular thing as well. From this particular expression, questions are asked. Now, guys, there is one more topic. What is that? You must have heard about it. That is Arrhenius equation. Have you heard about Arrhenius equation? Have you heard about Arrhenius equation? Arrhenius equation. Arrhenius equation which tells you exactly what happens to rate constant of the reaction on changing the temperature. What happens to rate constant of the reaction on changing the temperature. Okay? See, guys. First of all, for example, I have got the reaction A gives B. Let's say this is the reaction A gives B. Okay? Its order is, for example, N. Its order is, for example, N. Now, for example, I'm writing rate law for this reaction. Rate is equal to rate constant, concentration of A raised power N. Now, my dear students, first of all, if concentration of reactant is kept to 1 molar, at that point of time, rate of the reaction is rate constant. So, first of all, more the rate constant of the reaction, hence more is going to be the rate of the reaction. Now, if you remember, rate constant depends on the temperature. Rate constant of a particular reaction, it depends on the temperature. And how it depends on the temperature? That is something which Arrhenius equation is going to let us know. I'm directly going to give you the expression. Rate constant of the reaction, it is directly proportional to E raised to the power minus EA divided by RT. It is directly proportional to E raised power minus EA divided by RT. If you remove the proportionality sign, it becomes a constant A, E raised power minus EA divided by RT. This is one of the forms of the Arrhenius equation. Now, guys, in this particular expression, what this K is, what this EA is, what this R is, what this K is, you should first of all know their meaning. What is K? K already you know, that is the rate constant of the reaction. What is A? A is called as pre-exponential factor. You call it either as pre-exponential factor or you call it as the frequency factor. Right? Now, EA is something which you call as activation energy. My dear students, A and EA combinedly, they are called as Arrhenius parameter. Now, you tell me one thing. You have got a reaction which is carried out at temperature T. You have got a reaction A gives B. Assume that the reaction is carried out at temperature T. Its rate constant is K. Now, for example, if you increase the temperature of the reaction, tell me what will happen to the value of EA divided by RT? This value. If you increase the temperature, that means denominator you are increasing, this whole term will decrease. If this term is decreasing, that means minus times EA by RT. This whole term now will be increased. If this whole term is increasing, what does that mean? That means E raised power minus EA divided by RT. This whole term will be also increased. If this term is increasing, this whole term is increasing, which eventually says that K is increasing. So basically what is happening? We are increasing the temperature of the reaction, and on increasing the temperature, what is happening to the rate constant? Rate constant of the reaction is increasing. That's your Arrhenius equation. So Arrhenius equation says that on increasing the temperature, what happens to the rate constant of the reaction? Rate constant of the reaction increases. And do remember, in case of reversible reactions, upon increasing the temperature, rate constant of forward as well as rate constant of backward, both the things will increase. In case of reversible reaction, upon increasing the temperature, rate constant of forward as well as rate constant of backward reaction, both the things will increase. Point number one. Point number two, we got to know Arrhenius equation. K is equal to AE raised power minus EA by RT. Correct? Okay. K is equal to AE raised power minus EA by RT. So basically you got to know on increasing the temperature, rate constant of the reaction increases. And if rate constant increases, that means rate of reaction automatically increases. Right? Rate of reaction automatically increases. Now, my dear students, there are few more things. There are few more things which I want to discuss with you. For example, you have got a reversible reaction. You have got a reaction like this. A, for example, in equilibrium with B. Rate constant of the forward reaction, for example, that's Kf. Rate constant of the backward reaction, that's Kb. Okay. We got to know on increasing the temperature, rate constant of reaction increases, be it forward, be it backward. If you increase the temperature, rate constant of forward as well as rate constant of backward reaction, both the things increase. Okay. Now there is something which I want to share with you. My dear students, I'm going to write one equation. The equation is like this. Van 't Hoff equation you would have somewhere seen. Log of K2 divided by K1 is equal to delta H divided by 2.303 R. This is 1 divided by T1, or let me write it like this. This is T2 minus T1 divided by T1, T2. Well, I have taught this equation in the Le-Chatelier principle as well, if you remember, right? This particular equation. Why am I writing this equation? Because it's going to let me know about certain important things. It is going to give me certain important things. Imagine this is the reaction which we have, okay? So first of all, I'm assuming this particular reaction. It's equilibrium constant. K1, this particular reaction, its equilibrium constant is K1 when the reaction is carried out at temperature T1. When this particular reaction is carried at temperature T1, its equilibrium constant is K1. This is something which I'm assuming, right? Similarly, its equilibrium constant, for example, is K2 when the temperature of the reaction is T2. When the reaction is carried out at temperature T1, its equilibrium constant is K1. When the reaction is carried out at temperature T2, its equilibrium constant is K2. Now, in general, if I ask you what is equilibrium constant? Equilibrium constant is nothing. It is rate constant of forward divided by rate constant of backward reaction. Something which you already must be knowing. Correct? Now, guys, here the points are. What are the points? See, what are the important points? Imagine that this particular reaction is endothermic. Imagine that this particular reaction is endothermic in nature. If this particular reaction is endothermic in nature, that means its delta H has to be positive. Its delta H has to be positive. Imagine that this particular reaction is endothermic, so its delta H, it has to be positive, right? Now guys, understand. Delta H for the reaction is positive. I'm assuming that. Okay. Now, for example, you're increasing the temperature of the reaction. You're increasing the temperature of the reaction. If you're increasing the temperature of the reaction, then T2 minus T1 value, final temperature minus initial temperature, will come out to be positive. So T2 minus T1, it will come out to be positive. This value was already positive. Now this value is also coming out to be positive. So positive and positive makes it positive. That means log of K2 divided by K1, it is coming out to be positive. When is the log of x positive? When x is greater than 1. That means k2 divided by k1 here has to be greater than 1. Okay. What does that mean? K2 divided by k1 has to be greater than 1. That means k2 value has to be greater than k1. What is k2? K2 is the equilibrium constant at temperature T2. K1 is the equilibrium constant at temperature T1. So what it means? It means when we increase the temperature, equilibrium constant increased automatically. So do remember, for an endothermic reaction, equilibrium constant is directly proportional to temperature. But this is valid for endothermic reactions. Now comes the point. What is equilibrium constant basically? It is equal to rate constant of forward reaction divided by rate constant of backward reaction. Now you got to know that on increasing the temperature, equilibrium constant increases. On increasing the temperature, equilibrium constant increases. Does that mean Kf increases and Kb decreases? Does that mean Kf increases and Kb decreases? No. Why is that? I've already told you, on increasing the temperature, rate constant of forward and backward reaction both increases. That's something which is already discussed. On increasing the temperature, this term increases, even this term increases. If this is increasing, this is increasing, then how this particular term will increase? This particular term will increase only on increasing the temperature. Equilibrium constant will increase only if the increase in the value of Kf will be greater than that of increase in the value of Kb. Do remove this particular point. This is important, which I wanted to share with you. Okay, this is important, which I wanted to share with you. Right? Okay. So do remember, when it comes to endothermic reactions, in case of endothermic reactions, conclusions which you have to remember. In case of endothermic reactions, upon increasing the temperature, equilibrium constant increases. And upon increasing the temperature, rate constant of forward as well as backward reaction increases. Right? Which is possible only if the rate constant of forward reaction increases by larger amount as that of increase in the value of Kb. Yes, this is one important point which you have to remember. And similarly, you can check for exothermic reactions as well, right? Same procedure, you can check for exothermic reactions as well. For example, let me teach you for exothermic reactions, then automatically all these things will go into your head properly. See, for example, you have got the reaction A gives B. Rate constant of forward reaction is Kf, rate constant of backward reaction is Kb, correct? Let's assume K1 represents the equilibrium constant of the reaction at temperature T1. K2 represents the equilibrium constant of the reaction at temperature T2. Okay, right? And already we know what is equilibrium constant. Equilibrium constant is nothing. It is just the ratio of rate constant of forward and that of backward reaction. It is the ratio of the two. Now, try to understand. For example, assume that this particular reaction is exothermic. If this particular reaction is exothermic in nature, what does that mean? That means delta H value has to be negative. Delta H has to be negative, right? If reaction is exothermic, means delta H is negative. Delta H is negative. Now, imagine that you are increasing the temperature of the reaction. If you increase the temperature of the reaction, therefore T2 minus T1 value will come out to be positive. If you increase the temperature of the reaction, T2 minus T1 is coming out to be positive. T2 minus T1 is positive. This term is negative. So positive negative makes it negative. That means the log of K2 by K1 is negative. That means the log of K2 divided by K1 is what? It is negative. Which is possible only if K2 divided by K1 value will be less than 1. Which is possible only if K2 is less than K1. What can you conclude from here? What can you conclude from here? Check it out. You can conclude one thing. That on increasing the temperature, equilibrium constant, is it increasing or decreasing? It is decreasing. So, in case of exothermic reactions, what do you have to remember? In case of exothermic reaction, equilibrium constant is inversely proportional to temperature. Right? Sorry. In case of exothermic reactions, equilibrium constant, that is inversely proportional to temperature, right? Now, what does it mean? It means when you increase the temperature, what happens to equilibrium constant? Equilibrium constant decreases. But equilibrium constant is basically Kf by Kb, right? Equilibrium constant is basically Kf by Kb, right? On increasing the temperature, equilibrium constant decreases. Does that mean this value decreases and this value increases? Then only Keq will decrease? No, that's not the case here. See, on increasing the temperature, rate constant of forward as well as backward reaction increase. If this is increasing as well as this is increasing, and Keq has to decrease. How Keq will decrease? KEQ will decrease only if increase in the value of KB will be more than that of increase in the value of KF. This is the point which I want you guys to remember. Yes? Perfect. I hope this point is clear. Is this point clear to you? Right? So there are few things which you have to remember. In case of exothermic reactions, on increasing the temperature, equilibrium constant will decrease, right? And at the same time, increase in the value of Kb will be more than that of increase in the value of Kf. Why is that? Why is it happening? There is one more logic behind that. That is activation energy. I'm not going into that logic, etc., right? Leave that part aside. That's the graphical reason. Okay? I'm leaving that part aside. You just have to remember these points, which I told you right now. Now, guys, I'm going back to the Arrhenius equation. What is Arrhenius equation? K is equal to A e raised power minus Ea by RT. Perfect. This is one of the forms of Arrhenius equation. Are there some other forms of Arrhenius equation too? Yes, there are some other forms of Arrhenius equation too. My dear students, for example, I'm multiplying this equation with ln. It becomes ln of K is equal to ln of A multiplied by e raised power minus Ea by RT. Right? So it becomes ln of K is equal to ln of m into n is ln of m plus ln of e raised power minus Ea by RT. Perfect. Or you can write it like this. Ln of K is equal to ln of A. Ln of m raised power n is n ln m. So minus Ea divided by RT will come to the front. Then ln E is 1. So this is one more equation. This is one more form of Arrhenius equation. Minus Ea divided by RT type. Right? Similarly, you can convert it into the logarithmic form as well. You can write log of K is equal to log of A minus Ea divided by 2.303 R multiplied by 1 by T. This is one more form of this particular equation. These are different forms of Arrhenius equation which can be asked. Right? Yes, Anish, that's enough. That's more than sufficient. This is the first form of Arrhenius equation. This is the second form of Arrhenius equation. And this is the third form of Arrhenius equation. Right? Now, my dear students, there is one more thing which you have to remember about Arrhenius equation. What is that? One more form. Have a look. Guys. For example, you have got a reaction A gives B. Right? At temperature T1, assume that its rate constant is K1. At temperature T2, assume that its rate constant is, for example, K2. I'm assuming things. At temperature T1, rate constant K1. Temperature T2, rate constant is K2. Okay? Now, my dear students, if I introduce this particular condition into this equation, what do I get? I'll be getting log of K1 is equal to log of A minus Ea divided by 2.303 R. Now it's going to be 1 divided by T1. Correct? Now what I'm going to do, I'm going to introduce this condition into the same equation. It is going to be log of K2 is equal to log of A minus Ea divided by 2.303 R multiplied by 1 upon T2. Correct? If I do, for example, log of K2 minus log of K1, log of K2 minus log of K1 will eventually be log of K2 divided by K1. Right? Subtracting log of K2 minus log of K1. Log of A gets cancelled out. So my final equation becomes something like this. Ea divided by 2.303 R, it's going to be 1 upon T1 minus 1 upon T2. This is one more form of the Arrhenius equation from which the questions can be asked. One more form of Arrhenius equation from which the questions can be asked. Right? From which the questions can be asked. Right, guys? Is it clear? Is it clear to everyone? This is one more form. This is the fourth form. Now there are different forms. There can be different graphs as well based on Arrhenius equation. The first graph will be something like this. I'm writing ln of K versus 1 by T. What do you think ln of K versus 1 by T graph will look like? See, the equation is ln of K is equal to ln of A minus Ea divided by R multiplied by 1 by T. Correct? This is the equation. right? Now, ln of k you are plotting along y-axis, 1 by t you are plotting along x-axis. So this has to be your m, the sign is minus, and this is c. Y is equal to minus mx plus c. The graph is like this. What about the slope of this curve? Slope of this curve is equal to minus EA divided by R. What about the intercept? Intercept is C basically, and C is nothing, that's ln of A. Correct? This is the first graph. This is the first graph. Second graph. For example, you have to plot a graph between log of K, log of rate constant versus 1 by T. Again, which equation you'll be using? You'll be using this equation. Log of K is equal to log of A minus EA divided by 2.303 R multiplied by 1 upon T. Now, log K you are plotting along y-axis, 1 by T you are plotting along x-axis. This is your M, the sign is minus, and this term is equal to C. So y is equal to minus mx plus C. Graph is again like this. What about the slope of this graph? Slope of this graph will be simply minus EA divided by 2.303 R, and intercept of this particular graph has to be log of A. It has to be log of K. So these are the two graphs which you have to remember. That's all. Now, how many different types of questions can be asked? Let's have a look. Let's have a look how many different types of questions can be asked. Or before solving the questions, let me tell you just one more important thing. Just a second. One more important point. Do remember, on increasing the temperature by 10 degree or 10 Kelvin, for example. If you increase the temperature of the reaction by 10 degree, what happens to a rate? Rate of the reaction doubles. Rate of the reaction doubles, or even becomes more, or becomes even more, or becomes even more. When you basically increase the temperature of the reaction by 10 degree, or you can say by 10 Kelvin, do remember, the rate of the reaction, it doubles. It is basically the rate constant which doubles, or even becomes more. Eventually, rate of reaction increases. So my point here is, for example, you have got the reaction A gives B. You have got the reaction which is A gives B. When the reaction was carried out at temperature T Kelvin, for example, its rate constant was, for example, K. Its rate constant was, for example, K. Now I'm increasing the temperature by Kelvin. I'm increasing the temperature by 10 Kelvin. Now the temperature of the reaction is T plus 10 Kelvin. Now the rate constant would have doubled or even becomes more. Let's say the new rate constant of the reaction is now 2 times K. Is now 2 times K. My dear students, I'm defining a term, temperature coefficient, which I'm representing with N. Temperature coefficient. Temperature coefficient is nothing. It is the rate constant of the reaction. It is the rate constant of the reaction at temperature T plus 10 Kelvin divided by rate constant of the reaction at temperature T Kelvin. At temperature T Kelvin. See, this particular term is 2 times K. This particular term is K. So K cancelled, the value came out to be 2. So temperature coefficient of majority of the reactions, what you'll observe temperature coefficient of majority of the reactions will be 2. Right? But I told you, when you increase the temperature by 10 degree or 10 Kelvin, rate constant doubles or even becomes more. Over here, I've exactly considered that rate constant is doubling. It can be 2.1 also. It can be 2.2 also. Right? If it is 2.1 K, then the N value will be 2.1. If it's 2.2, N value is 2.2. So in general, N value, it is greater or equal to 2, but it is less than 3. Temperature coefficient value, it is greater or equal to less than 3. Right? Okay? Do remove this particular thing. This N is something which you call as temperature coefficient. This is called as temperature coefficient. Okay? Right? Now, guys, one more thing which can be asked. One more thing which can be asked. For example, you have got the reaction like this. A gives B. A gives B. Okay? A gives B. At temperature T1, assume that the rate of reaction is R1. At temperature T2, assume that the rate of reaction is R2. Right? At temperature T1, when the reaction is carried out at temperature T1, the rate of reaction is R1. When the reaction is carried out at temperature T2, the rate of reaction is R2. Now do remember, R2 divided by R1 is equal to, it will be 2 raised power T2 minus T1 divided by 10. This is one more expression from which question can be asked. One more expression from which question can be asked. For example, I'm giving you a question like this. Let's say the reaction is A gives B. The temperature of the reaction is, for example, 10 degrees centigrade, right? The temperature of the reaction is 10 degrees centigrade. Now you are increasing the temperature from 10 degree to 100 degrees centigrade. I'm asking you how many times rate of reaction has increased. You're increasing the temperature. On increasing the temperature, rate constant increases. Eventually, rate of reaction increases, right? So this is temperature T1, this is temperature T2. Let's assume at temperature T1, the rate was R1. At temperature T2, the rate is R2. So what you'll write? R2 divided by R1 is equal to 2 raised power. T2 minus T1, that's 90. 90 divided by 10 is 9. So new rate of the reaction will be equal to raised power 9 times the earlier rate of the reaction. I would say rate of the reaction has increased by this much of amount. Right? Okay. Perfect. Do remember this particular expression as well. So this particular expression is going to let you know upon increasing the temperature how many times rate of reaction will increase. That's all. How many times the rate of reaction will increase. Yeah. Right, guys? Look at this particular question. Look at this particular question. The question is calculate the activation energy of the reaction. Graph is given. Graph is given. Activation energy is to be calculated. Graph is between log K versus 1 by T. If you remember, few minutes back only I told you what is the slope of log K versus 1 by T. It used to be, I believe, minus EA divided by 2.303 R. Right? And what is the slope of this curve? Slope of this curve is tan of theta. We are given theta is equal to tan inverse minus 3. What does that mean? That means tan theta is equal to minus 3. Slope is basically tan of theta, which is minus EA divided by 2.303 R. Right? Tan of theta value will be equal to minus 3. So minus 3 is equal to minus EA divided by 2.303 R, or you can say EA will be equal to 6.909 R. EA, activation energy, is equal to 6.909 R. Now, the first question says, calculate the activation energy in kilojoules per mole, right? So, EA will be equal to 6.909 multiplied by R value I'll be using is 8.314 joules per Kelvin per mole. Since I'm using the R value in joules, so the whole term right now is going to be in joules, but I have to get in kilojoules. Divide by 1002, the answer you'll be getting in kilojoules. The second question, get the answer in kilocalories per mole. Activation energy has to be equal to 6.909, right? R value you'll be writing as 2 calories per Kelvin per mole. This whole term right now will be in calories. Now divide by 1000. Now this answer is going to be in kilocalories, right? So both equations are done and dusted. It is just by looking at the slope you solve the equation. By looking at the slope you solve the equation. Simple. Yeah. Look at this particular equation. The rate constant of the reaction at this temperature and this temperature are this and this. Calculate the activation energy. Isn't it simple? The rate constant of the reaction at temperature T1. T1 temperature. This is T1, this is T2. But convert them into Kelvin. T1, T2 is given. K1, K2 is also given. T1, T2 is given. K1, K2 is given. Calculate the activation energy. Isn't it simple? T1, T2 is given, right? And K1, K2 is also given. R value already you know 8.314. One equation, one unknown. So activation energy you can calculate easily, right? This is simple formula based equation. Nothing else. Nothing to do here. Nothing to do here. Nothing to do here. Nothing to do here. There was one question asked long back. I don't exactly remember the question, but the question was something like this. The correct form of Arrhenius equation among the following is. The correct form of Arrhenius equation among the following is. Just a second. There were a few options which were given. First option was d upon dt of ln of k is equal to EA divided by RT square is equal to EA divided by RT square. This was the first option. Second option was integral of d upon dt of ln of k is equal to minus EA divided by RT square. Like this, a lot of options were given basically, right? Like this, a lot of options were given. Now, my dear students, how do we get the correct answer? See, Arrhenius equation is what? One of the forms is ln of k is equal to ln of A minus EA divided by RT, right? Now, what you are doing in all the things basically, you are differentiating with respect to temperature. So, differentiate with respect to temperature. So, d upon dt of what? D upon dt of ln of k. You are differentiating with respect to temperature. It's a constant, its differentiation is 0. Now, differentiation of 1 by t is minus 1 upon t square. Minus comes to the front. So, it simply becomes EA upon RT square. So, this is one more form of the Arrhenius equation, which was asked long back in the questions, right? I just differentiated the Arrhenius equation with respect to temperature and got the result, right? Clear? Clear, people? Okay, so this was your Arrhenius equation. There is one topic left, that is collision theory, but I don't think I'll be able to take collision theory now. I'll be posting a recording on collision theory. Okay, that will be like half an hour concept, half an hour topic. I'll be posting the recording soon. Right? So one topic is left here, that is collision theory, half an hour topic that is. You can, if anyways, you can do that from NCERT as well. If not, I'll be providing you one recording of that particular topic. And with that, the chapter is over. Okay? Perfect. So with this, this kinetics chapter is done and dusted also. Yes, I mean, after reading all these lectures, just go through your NCERT once, right? Just read NCERT once for kinetics, that's sufficient. Perfect, guys. So with this, I'll be taking a leave then. Okay. So our one more chapter is done and dusted. That is chemical kinetics, right? So day after tomorrow, what we shall be doing? We shall be doing IUPAC nomenclature, right? And tomorrow there is an amazing surprise coming up for all of you. Do join that session at 10 p.m. tomorrow. You are getting something interesting. Yeah? Chalo. I'll be taking a leave with this. Take care. God bless you all and bye, guys.